Dr. Kavinder, as you told, member, Steering Committee, Ministry of Electronics and Communication. Ajay ji from Intel. Mukesh Ranjan ji from IPR. And several names, Dr. Rajinder Dhaka from IIT Delhi, Professor Murugal ji from Delhi University, Professor Hasmi ji from Delhi University, and several names I may have forgotten, Ma'am Mukta from CSR Hyderabad, SD Kaushik, Kuldeep ji from Kekri CSR Chennai, and several other dignitaries. I may not be able to mention the name. Dear participants, invited speakers, and students, media persons, and supporting staff, without whom this is not possible. I can see Akhilesh Mishra from my friend from IIT Roorkee, Bharti Singh from DTU, and several other dignitaries. A very good morning to all, and a very warm welcome to this conference. It is my great privilege and honor to welcome you all to the International Conference on Photonics and Emerging Materials for Futuristic Technology 2025, organized by the Department of Physics, Chaudhary Charan Singh University, Meerut, during November 13 to 15, 2025. This conference marks yet another milestone in our department, rather I should say the university, ongoing pursuits of academic excellence, research innovations, and global collaborations. The theme, Photonics and Emerging Materials for Futuristic Technology, truly reflects the forefront of contemporary scientific endeavors. Today, photonics is reshaping the technological landscape, powering applications ranging from quantum computing to high-speed communication systems to the removable energy and biomedical diagnostics. Simultaneously, emerging materials are revolutionizing our understanding of light-matter interactions. Through this platform, we aspire to bring together leading scientists, technologists, industrialists, academicians, and young researchers from across the globe to share their insights, exchange ideas, and foster collaborations that may define the next generation photonics and material technology applications. I take this opportunity to express my heartfelt, deepest gratitude to our chief guest, Dr. Parimal Kumar ji, for gracing this occasion despite his demanding schedule. Let me mention here, I just called him 3 days back and he got ready to come here. Sir, we are very thankful to you for your kindness and gentleness. Your distinguished presence inspires all of us, reinforces the strong linkage between scientific research and national technological advancements. I am also grateful to Dr. Meena Mishra ji, Director SSPL. Over the course of more than 3-4 years, significant contribution to the sector research and tirelessly developed gallium arsenide with MEMS technology. Madam, we are also grateful to you that you agree to be distinguished guest here, and also she is generous to deliver a keynote talk followed by this inaugural session. I am grateful to Dr. Vipin Shukla from bottom of my heart, because whenever I stuck with anything in life, in network and anything, he always come forward and hold my hand, and he spare time to hear to this inaugural. So I am very thankful to him. I will not use very much words for him because he is also a good friend of mine. So it will be better to least communicate about him. I extend my sincere thanks to our Honorable Vice Chancellor, Professor Sangeeta Shukla Madam, for her visionary leadership, constant encouragement, which have made this event possible. Madam always available whenever we put any proposal from our department. It is necessary to mention here, Madam always hold our hand. Oh, this is physics department. I do not have any question. So, Madam, thank you very much. You spare time here. Every time you give financial support, logistic support, whatever support you need, she always there to support us. The central theme of PMFT 2025 is Photonics and Emerging Materials for Sustainable and Intelligent Future. The theme fulfills almost 70% of the goal, Sustainable Development Goals. That is what the Indian government is looking for right now. The conference will provide multidisciplinary platform to explore new frontiers in sensors, photonic devices, and quantum materials. Discuss the role of emerging nanomaterials and in energy conversion, storage, and environmentally sustainable development. Foster academic industry collaboration for developing next generation materials and devices for social benefit. More than 25 delegates are expected to participate in this conference. The event has eminent speakers from USA, from UK, from Portugal, Germany, Serbia, Slovenia, UAE, South Korea, and in India from BARC Mumbai, IPR Ahmedabad, CSIR NPL New Delhi, CSIR IICT Hyderabad, CSIR KECRI Chennai, DRDO SSPL, IIT Delhi, IIT Roorkee, IIT Ropar, NIT Warangal, NIT Hamirpur, NIT Srinagar, and Jawaharlal Nehru University New Delhi, Delhi University New Delhi, Central University Rajasthan, Central University Kerala, Central University Gujarat, Rajiv Gandhi Central University Arunachal Pradesh, and various other state universities. I cannot basically mention the name here, it is too long. Our 3 days, the conference will include 2 keynote lectures, keynote addresses, 67 invited lectures, 30 oral presentations, and more than 60 poster presentations. There will be more than 30 sessions, including 8 parallel sessions, technical sessions, 1 poster session, 1 inaugural session, 1 valedictory session, 1 cultural session, and 2 panel discussions on material for sustainable energy production and storage covering, and second session will be photonics and quantum technology. These sessions will cover diverse topics such as photonic crystals, metamaterials, 2D materials, nanophotonics, batteries, supercapacitors, and materials for environmental remediations, and hydrogen production, etc., etc. A special industry academia interaction session focusing on traditional research and startup opportunities in photonics and advanced materials will also take place. Once again, I welcome all our guests, speakers, and delegates to PEMFT 2025. May this conference serve as a beacon of inspiration and catalyst for innovations in photonics and material sciences. Jai Hind, Jai Bharat. So I also have an announcement for the participants. There are 2 barcodes on your iCard. So whenever you want to look for a schedule, you can scan that. Schedule will be on your mobile. And also the conference booklet barcode is there. You can scan that, and your conference booklet will also be on your mobile. Thank you very much.
Thank you very much, sir. So now it's the time to release of the abstract book. For this, I would like to request our esteemed dignitaries to officially release the abstract book. Ladies and gentlemen, this is the most significant moment of today's proceedings, the release of abstract book for the conference. This book encapsulates the rich collection of research papers and presentations that will be shared and deliberated upon during these 3 insightful days. Thank you very much for doing the honors. I would now like to invite Professor Birpal Singh to the stage to share insights into some of the key R&D achievements of our university.
Thank you, Dr. Kavita, and very good morning to one and all present in this Atal Sabhagar and obviously connected online. Honorable Vice Chancellor, Professor Sangeeta Shukla of this university, our most important person of this conference, the chief guest, Dr. Parimal Kumar, outstanding scientist and scientific advisor to Chief of Integrated Defence Staff, Ministry of Defence, Government of India. Our 2 distinguished guests, Dr. Meena Mishra ji, the Director, Solid State Physics Laboratory, New Delhi, and of course Dr. Vipin Shukla, the Head, Department of Scientific and Industrial Research, New Delhi. Dr. Devasi Bhai Adoja from UK, our senior most professor, Professor Mridul Kumar Gupta from Department of Mathematics and former Pro Vice Chancellor of this university. My fellow colleague, Dr. Anil Kumar Malik, the Head Department of Physics, Deans and Heads of different faculty of this university, and the most important again, the esteemed speakers, I am not naming their name, of this conference, members of organizing committee, and my fellow colleagues and research scholars of the department and faculty members of other departments. I am seeing number of faculty members and heads are attending this inaugural session of this international conference of this university and affiliated colleges also, and dear participants and media person. On behalf of organizing committee, I welcome you all in the inaugural session of International Conference of Photonics and Emerging Materials for Futuristic Technology. As Professor Malik told, which is really very relevant and aligned with the most of the goals of FDGs and even the vision of Viksit Bharat at the rate 2047. The Department of Physics is the oldest department of this university, and it's a DST FIST supported department which has state-of-art experimental research facilities. In addition to sophisticated experimental facilities like SEM, SEM, AFM, RF DC magneton sputtering system, even spin coating units, number of spin coating units, and one wonderful research facility we are having in our department, that's the nano imprint lithography setup with 10,000 clean room research facilities. Chemical processing facilities, number of UV visible spectrophotometers, micro Raman spectrophotometer, and crystal growth facilities, gas sensing facilities, electrochemical measurement facilities. The Department of Physics has also established an advanced computational facility that is funded by SARB DST New Delhi. As Dr. Kavita has mentioned, being Director Research of this university, I should say something all about the recent achievements of this university to this August gathering of academicians that really we achieved under the dynamic and visionary leadership of our Honorable Vice Chancellor, Professor Sangeeta Shukla ji. We all know that this university is accredited by NEC, and that's A++, the highest grade given by NEC. And it's again a matter of proud for me just to share with you that in NEC, this university is securing 3.66 CGPA out of 4. That's really a very remarkable achievement. We achieved this by the leadership of our Honorable Vice Chancellor. in the Times Higher Education ranking, that's called D ranking, and that's a World University Ranking 2026. In the history of this university, we attained this rank first time under the leadership of again our Honorable Vice Chancellor. As a consequence or as a result of that kind of rankings and accreditation, we received rupees 100 crore grant under multidisciplinary education and research university under the scheme of Meerut under PM USA project. We are also among top state university of Uttar Pradesh as we received Research Excellence Citation Award by Clarivate and Above Science in two categories. One is under State University category and second is under Women in Research category, and one of our professor, Dr. Saru Kumar from Department of Mathematics, he received that award under the category of Women in Research in the whole country. Obviously, we are doing well in research, so as a result of that, we are at top. I'm saying in Best University Ranking 2025 in all government universities of Uttar Pradesh of this state, and we are ranked at 17th in India by India Today MDR ranking 2025. And in addition to common research, we are also producing good number of IPRs, and as a result, we are at 4th rank in India among government universities in patent granted in 2023. And last year we were at 5th position in India among government university in patent granted. So as a consequence of again this achievement, we have received IPR chair from Ministry of Commerce and Industry, Government of India. We are at 219th rank in Southern Asia in QS World University Ranking 2024. And we are again, as I told you that most of the credentials and achievements are related to research. So in that is, we are first in UP and we are 29th in India in SIMAGO Institutional Ranking 2025. We are first again in UP and we are at 66 in India among top 100 STM institutions, and that has been given by Chronicle of India STM ranking 2025. Our country rank is 139 in a very prestigious ranking given by Spain, and that called Webometrics ranking in 2024. Our H index of last 5 years is really very excellent, and that is 6, and our field weighted citation impact is 124, and our citation per publication is 12.2. That's very impressive again. Our highest impact of 42.5 and more than 37.3% of our public rating journals. That are really very good thing for public this university. As I mentioned earlier, that the theme of conference is very relevant and aligned with SDGs and the Viksit Bharat goal. So I'm sure that this conference will definitely be beneficial for both theoretical scientists as well as experimentalists of this country as well as across the globe. I'm very thankful to our university administration, especially our Honorable Vice Chancellor, for giving all necessary approvals for this conference. And I am also thankful to different funding agency, namely the DSIR, and head of the DSIR is really present in this conference also. We are also thankful to DRDO. Number of scientists are attending this conference from DRDO. Madam is over here. We are thankful to ANRF. We are thankful to, and even we are thankful to our industry collaborators, that's Ricago and IR Tech, for their financial support. At the end, again, I would like to welcome all learned speakers. I have not mentioning their names, but I know most of them, delegates and guests of this conference, with the hope that the lectures, the deliberations, and the discuss the conference will really boost your academic and scientific temper. With these words, once again, thank you all. Jai Hind, Jai Bharat.
Thank you very much, sir, for your enlightening, highlighting the remarkable achievements of our university. With great pleasure and utmost respect, I invite distinguished guest Dr. Vipin Shukla to share his valuable thoughts and insights with us.
expert dais of the dais, and most important, the ignited mind of the country. About CSIR lab that comes under DSIR, and beside this we have some public sector enterprises also. And one is Central Electronics Limited, which is in Ghaziabad. That is a public. And there are 4 different schemes which will run. I'll not go into the detail because we are running out of the time, but I will name the schemes and I'll request to give brief about 1-2 sentences, and I'll request if someone is interested. Supported, and also one study we have supported. So that 80K plus scheme is interesting scheme for you. Quality of another is we create a hub which is called as Common Research and Technology Development CRTDH, and which is primarily established in academic or research institute with an objective that you should promote more and more R&D culture among MSMEs. So what, it's not for academic research, but it is for industrial research, and we have 18 such centers, and you can also take advantage of that. So this is something which I thought I should share with you, and if anyone feels he or she can be interested. Now, when we talk about some of the schemes, you'll go through our website, you'll see that we focus much on industrial research and primarily on MSMEs. So MSMEs is one of the major stakeholders for us, but at the same time, all these hand-holding to MSMEs is done through academic or research institutes, because we cannot directly support to MSMEs, so we support to academic or research institute, and they handhold MSMEs. Now, some of the facts which I'll share with you so that you can also feel good and proud, and then you can ignite your mind to do more and more. And this is especially for young people. So, you know, we have, how many unicorns we have right now? Around 120 till now we have unicorn. And if you don't know what is unicorn, then you should go through all these things. Because there was a time 10 years back when, forget about unicorn, we even did not have startups. It was around 500 startups in the country. But in last 10 years, we have around more than I think around 2 lakhs proper startups we have. We have 120 unicorns with us. And also, we are not talking about unicorns, which are also reaching towards to become unicorn. And all these things I want to tell you because sometimes we feel that unicorn or startups are being established by highly ranked institutes like in India if you say IITs or IIM, but it's not like that. If you see some of the data, very interesting data, if you talk internationally, IITs, this system is on the 4th number as per some of the data. It is in the 4th rank among all global agencies, if you consider Harvard and any other. So that shows that India, we are doing equally good, first thing. Second thing, if you come to Indian data, that shows that yes, some of the ITs, IIMs, they are doing good, but there are out of 115 startups from one data I got this information that 7 dropouts are also running unicorns. That shows for running unicorns or startups, you should have an idea rather than you should have a high degree or qualification, but you should have a proper idea, you should have a proper team. And be very clear that when we talk about a startup, alone you cannot move ahead. You have to build a proper team, which may include technical people, which may include financial, which may include legal, which may include IP-related experts, so that you can protect your idea also. So data shows that there are possibility and opportunities for everyone in this field. Now, another interesting fact which I got, like if we talk, if I ask you that which state is doing good, you can say, okay, in a startup, which city if I say, so you can say Delhi, Mumbai, Bangalore, all these things. But surprisingly, if you see a data from one of the sources, it says that UP is doing very good. If we talk about the founders of the startup unicorns. Now, if you go to Karnataka, the number is very less. That is very surprising fact, because we know that all startups, unicorns, and IT-related, technology-related things are in Karnataka more than UP. But what happens that anybody who is related to UP, ultimately he goes to Karnataka, because everyone wants some favorable environment. So that may be one of the reasons why most of the people think that founders of unicorns are primarily from big cities, but it's not like that. Most of them are from UP and other states whom we don't think to be torchbearer of unicorns or startup area. Now, very soon by 2030, we may have around 300 or 280 unicorns that is predicted. So you have a lot of opportunity to look into that. I know I'm running out of time. Am I right? So I have something, but one thing I want to just throw in front of you, you think about that. If you can catch something, well and good. Otherwise, you go and do Googling and try to understand. There are few countries whom I will refer. USA. When we talk about USA, Silicon Valley comes in our mind. And obviously, then venture capital and risk-taking culture that exists in Silicon Valley comes in our mind. So that is their edge. So you have to think that we should also talk about venture capital and risk-taking ventures. When we talk about Germany, innovation-driven manufacturing, everyone knows about that automobile, the mechanical-related, manufacturing-related, Germany is doing a good job. So they have innovation-driven manufacturing. That is second takeaway. Third is Singapore. When we talk about Singapore, we know that digital transformation and policy efficiency, they are leading. And when we talk about Israel, government-backed R&D and startup nation model they are adopting, which is resulting in a technology torchbearer. And Israel, very interesting fact, very low population, very small area, but the thing is you name any technology, 70% of the founders are either from Israel or related in some way to Israel. And that happens because, very interesting thing, in military they have one unit which once they are retired, they immediately open up a startup. And most of the great pioneer technology which we are using, those are built up by those military people. They were, like in our language, they were Jawans of the Sena. And they are now founder of unicorn, they are founder of big companies. So these 4 countries I just summarized that they have some edge in some area. You are young mind, you have to think that how can you make your journey, especially when you plan about to start a startup or unicorn. So these are something which I thought I should share with you. I had much more things which I skipped, but once again I want to thank the organizers that I got this chance to share all these things with you, and I give my best wishes to the organizers and all of you for a very successful event 2 days, in coming 2 days. Thank you very much. Thank you.
We are truly grateful to you, sir, for letting us know the various research funding schemes sponsored by the DSIR in the shortest possible time and for gracing the occasion with your presence. With these words, with great respect, may I now request our distinguished guest, Dr. Meena Mishra, to please take the podium and share your inspiring thoughts with us.
A very good morning to all of you. And first of all, I would like to convey thanks to the organizing team that they have really done a wonderful job. I must congratulate the organizing team that so many people you have called, and all of them are, a known figure in their field. So for kids, I would like to say they have done a lot of hard work, but now it is time that you should learn from all those people who are going to speak for you. And then I would also like to tell our Honorable VC Madam, I'm really surprised. I'm flabbergasted. I really did not know that this university has achieved so much. For me, it was an eye-opener, and I really feel happy that today I'm here, and that is how I could come to know that this university has achieved so much. So I think a loud applause should come from your side for your university. You should be really, really proud of it. From my side, I'll give a lecture later on, but as have been introduced, that I am from semiconductors field, and right now is a time for semiconductors. So all those science grads who are sitting there, or post-grads, or the PhD students, I can only say, आप अपनी belt tight कर लीजिए. This is a time when you can be absorbed in the industry immediately. So ध्यान से पढ़िए, अच्छे से पढ़िए. There are 4 C's which I tell to all the kids wherever I go. There are 4 C's. If you will follow those 4 C's, definitely you will touch the sky. What are those 4 C's? Does anybody know? It is curiosity, commitment, clarity and consistency. आप अगर इन 4 C's पे ध्यान देंगे तो डेफिनेटली आप जहाँ पहुँचना चाहते हैं आप पहुँच जाएंगे। दूसरी चीज़ और कि अगर हमें कहीं पहुँचना है तो सबसे पहले हमको क्या निश्चय करना पड़ता है कि हमको कहाँ पहुँचना है, हमारा लक्ष्य क्या है। तो प्लीज़ अपना लक्ष्य साधिए, इन 4 C's को फॉलो करिए, डेफिनेटली आप जहाँ सोच रहे हैं उससे भी ऊपर पहुँचेंगे। एक चीज़ और जो मैं हमेशा मिस नहीं करती हूँ बच्चों को बताने से, वो ये है कि फियर ऑफ फेलियर हम सब में बहुत ज़्यादा होता है। उस फियर ऑफ फेलियर को छोड़ दीजिए। जब आप एक बार सोच लेंगे कि मेरी बहुत बड़ी टीम है, नॉर्मली हम कोई बड़ा काम लेने से डर जाते हैं। वो जो डर है, जो हमारे अपने दिमाग की उपज है, अगर आप उस डर को छोड़ देंगे तो आप कुछ भी कर सकते हैं। अभी आज की तारीख में हमारे देश के यंग बच्चों को इसी चीज़ की ज़रूरत है कि डर को छोड़ दें, कमिटमेंट के साथ, सच्चे मन के साथ पूरी ताकत लगा के काम करिए एंड सफलता डेफिनेटली, कोई डाउट ही नहीं है कि सफलता आपके पास नहीं आएगी। और ये आजकल का टाइम सेमीकंडक्टर्स का टाइम है। दे हैव चोजन अ वेरी ब्यूटीफुल थीम ऑफ फोटोनिक्स एंड इमर्जिंग मटेरियल्स, बिकॉज यही एक ऐसा एरिया है जिसमें हमको जैसे विकसित भारत 2047 की तरफ जाना है। 2047 में अगर हमको विकसित भारत चाहिए तो इसका मतलब हमको एक साउंड इकोनॉमी चाहिए। एक साउंड इकोनॉमी के लिए हमको सेमीकंडक्टर्स में अगर हम इंडिपेंडेंट हो जाते हैं, आत्मनिर्भर हो जाते हैं, तो हम उस हाइट को टच करने से हमें कोई नहीं रोक सकता। सो आज के आपने इतने सारे लेक्चर्स अरेंज करे हुए हैं एंड सब लोग बहुत बहुत अच्छे लोग हैं जो अपने अपने फील्ड के मास्टर्स हैं, जिन्होंने सालों काम करके ये सब कुछ सीखा है। सो इट्स अ वेरी गुड अपॉर्चुनिटी फॉर यू। प्लीज अटेंड इट प्रॉपरली एंड आस्क क्वेश्चंस, एज मेनी as questions you can ask, please ask। और ये एक मेरे जब मैं स्टूडेंट थी आपकी तरह वहाँ बैठती थी, मेरे एक प्रोफेसर ने मुझको बताया था कि अगर अभी क्वेश्चन नहीं पूछोगे तो कभी नहीं पूछ पाओगे, क्योंकि अभी तो आपको बच्चा समझ के अच्छा हो कि नहीं आता होगा, कोई बता देगा, बट एक बार जब जॉब में चले गए तो आपको खुद अपनी ईगो पे लगेगा, अरे मेरे को पूछना चाहिए कि नहीं पूछना चाहिए। सो दिस इज़ द बेस्ट टाइम, इसका पूरा आप अपना उसको एक्सप्लॉइट करिए, उसको यूज़ करिए और ज़िंदगी में आगे बढ़िए। थैंक यू सो मच।
बहुत बहुत धन्यवाद मैम आपका। So with immense pleasure and deep respect, I invite our chief guest Dr. Parimal Kumar to take the stage and grace us with your inspiring address.
जय हिंद। ऑनरेबल वाइस चांसलर चौधरी चरण सिंह यूनिवर्सिटी मेरठ, प्रोफेसर संगीता शुक्ला जी, डॉक्टर मीना मिश्रा, डायरेक्टर सॉलिड स्टेट फिजिक्स लेबोरेटरी DRDO, डॉक्टर विपिन चंद्र शुक्ला जी, हेड CRTDH पेस डिपार्टमेंट ऑफ साइंटिफिक एंड इंडस्ट्रियल रिसर्च, प्रोफेसर अनिल कुमार मलिक जी, कन्वीनर PEMFT 2025, डॉक्टर नीरज पवार जी, Secretary PEMFT 2025, distinguished faculty members, invited speakers, delegates, students, honored guests. I believe if there are media persons and all other participants. Dr. Adroja, Senior Scientist, Rutherford Appleton Lab, United Kingdom. So it is my proud privilege to address this august audience. Your presence underscores our collective resolve to address one of the most dynamic and consequential technological challenges both for civilian as well as military applications. In fact, today standing before you for this keynote address, I feel humbled. And I will also like to share the reason for why I am feeling humbled. I was a student of physics in my graduation, which I still believe to be, but not in a very active manner. I am not an active student. I did my BSc Physics from Regional College of Education, Bhubaneswar, which is a college of NCERT. I don't know how many of you are aware of the college. I learned that the college is now a deemed university. There I got a chance to study physics from one of the best professors, in my opinion, Professor M.A. Chandrasekhar, Professor J.K. Mahapatra, Professor Parida, and Professor Madhuri Mahapatra. The college had a very well-equipped physics department. I'll tell you why I'm telling all these things. And a very well-equipped library. I was doing reasonably well and wanted to pursue my career in physics. Thereafter, I joined Utkal University in my post-graduation, and there I got a chance to study from Professor Niranjan Barik. I don't know, many of you would have heard his name. He was a very popular professor. And there was Institute of Theoretical Physics in Bhubaneswar, where I wanted to pursue my career. I believe since this is physics today, perhaps some of you would have heard his name, and he was very popular. But then I came across a reality. When you reach to post-graduation, after graduation, getting a job becomes a reality and becomes a priority for most of the students, and this was applicable for me too. So I decided to move from MSc Physics to MSc Computer Science from Utkal University to University of Allahabad. While University of Allahabad is a very prestigious university with a legacy of more than 100 years, and computer science in itself was a very good subject, especially at that point of time from the job perspective, which has revolutionized our modern life. The reason for me to switch over to computer science from physics because of better job prospects was something which troubled me for a very long time. Later on, I accepted it, and we say, as in today's language, I moved on. Today, standing here in front of you for the keynote address, I believe many of the postgraduate students and young research scholars would be in the same situation. Is it true? Students, how many of you in the same position, doing MSc Physics, looking for a job, and maybe trying to switch over? So bright students of physics trying to switch over to other disciplines for better job prospects, and this is the reason I feel humbled for getting chance to be in the physics department of such a prestigious university after almost a period of more than 3 decades. So in my today's address, even though the topic suggested to me, or rather opted by me, is rising relevance of advanced research in photonics and material sciences for defense applications, which I'll definitely touch upon, but I'll also like to another key point which relates to augmenting career options for physics students without mandatory migration to other disciplines which offer better job prospects for fostering or augmenting their by augmenting the startup and entrepreneurial culture in the university in general and the physics department in particular. Now let us come back to the topic, rising relevance of photonics and emerging material for defense applications. Photonics, as you know, the science of light manipulation and advanced materials sciences is rapidly becoming central to modern defense technology. Innovation in these fields are transforming surveillance, communication, sensing, and protection systems essential for national security. The sophistication and adaptability of future defense platforms depend heavily on our ability to engineer new materials and photonic devices. Let us see what are the new frontiers in photonics for defense applications. Some of the upcoming areas in photonics for defense are photonic integrated circuits. This allows miniaturized multiplexed biochemical sensors that are portable and highly accurate, aiding in hazardous materials detection for military and homeland security applications. Programmable nano-optics represents a leap beyond static optical systems. These systems can be dynamically reconfigured, giving defense platforms adaptive surveillance and communication adaptabilities in the field. Then there are metamaterials. Engineered at the nanoscale, enable technologies like cloaking and compact polarization optics, pushing the limits of traditional defense applications. And as we know that the metamaterials are at the center of stealth capabilities, which is very important for defense. Then there are, let us see which are the revolutionary advances in material sciences. We saw in photonics, now in material sciences. Material sciences breakthrough directly impact the robustness, weight, and effectiveness of defense equipments. Emerging materials such as perovskites, and I have heard that it was discovered in 1939 or so. It is used mainly in solar cells and have been synthetically developed also, artificially developed. Quantum dots and two-dimensional structures offer tunable optoelectronic properties useful in photo detectors for imaging, monitoring, and secure communication. Then lightweight, ultra-strong armor materials, which is very important for defense applications, and composites are critical for troop and vehicle protection, while smart materials respond in real time to environmental changes. Advanced materials also form the backbone for next generation electronic and photonic devices, making sensors, weapons, and support systems more efficient and reliable. Defense applications, let us see some of the concepts from to battlefield. Applications in aerospace. Optical fiber sensors embedded in aircraft structures provide real-time monitoring, improving safety and mission readiness. Then let us see in submarines. Photonic devices ensure secure interference communication and interference-less communication and environmental monitoring under extreme conditions. Then optical communication. Near-infrared materials and broadband amplifiers enable faster, more secure data link across the battle space, vital for modern network-centric warfare. Stealth and camouflage. We saw the metamaterials, they help us. Metamaterials are leading to new generation of stealth, including adaptive camouflage and radar invisible materials, which we called as stealth also. Now, we have seen some of the applications, defense applications of photonics as well as advanced materials. Then why the relevance is rising? Because we have a national ambition of becoming self-reliant and a Viksit Bharat by 2047. If we want to become self-reliant in these areas, and as you know that we have dependence on some of the foreign countries, especially in rare earth materials and all. So if we want to become self-reliant, then it is becoming more and more relevant that we do research in these areas. And if we do not have the raw material on our own, can we develop the synthetic materials, alternative materials having similar properties or near similar properties, which can serve the defense applications. So its relevance is increasing more and more because we want to become the Viksit Bharat by 2047. And this push towards autonomous defense systems, artificial intelligence, integration, and quantum technologies depend on ongoing advances in photonics and material sciences. That's why it is becoming more and more relevant. I am from headquarter integrated defense staff, which we call the HQIDS. There's Army, Navy, Air Force, and this is the tri-services. You must have heard about theaterization. So that is the tri-services commands. And there we have the motto, victory through jointness. And that victory through jointness is not only applicable only in warfare, but it is also applicable in research. So interdisciplinary collaborations or jointness is the key for advancement. Chemists, physicists, engineers, and material sciences along with users are very important, are all crucial for bringing laboratory discoveries to real-world applications, especially defense applications. And as my earlier Dr. Shukla has spoken, some of the opportunities, there's IDX, TDF, these are the funding agencies for funding the defense-related projects. Now, so what are the career opportunities for our students and young researchers? In defense, I can tell you that joining armed forces is one of the best careers. It's not only, it is something which you say in Hindi, I like to speak in Hindi, that the Aan Baan Saan. If you want, that is in the armed forces. The kind of pride you get in serving the nation, it is not only a job, it is just service. ये एक नौकरी नहीं है, एक सेवा है. And joining armed forces is definitely one of the best career options. Then there are government organizations, other civilian organizations like DRDO. But the point is that finally at the end of the day, the number of jobs will remain limited. So what our students should do, and my predecessors, Dr. Shukla, has already touched on this subject. So I'll come up to that. There is something called as a culture. And the culture word which I define, that's the way of life. And as he was telling that we have today more than around 2 lakh startups, DPIIT recognized startups. So that kind of entrepreneurial culture and the startup culture, that has to come up so that we become from job seekers to job providers. And the roots of the entrepreneurial culture lies in the education and the universities like this. Roots lie in the education. Prior to independence, we had a system which is my college education system, which we say, and that was meant for developing clerks. But now the environment has changed, and this is one of the best time when we can have the startup culture or entrepreneurial culture. The startup culture began with opening of economy in 1991, and the software companies were the first movers. Gained momentum with Startup India, as already covered also. Lot of employment has gone, more than 12 lakhs. Nearly 50% from startups are from Tier 2 and Tier 2 cities. There are equal number of women also. So we can say that in a way it has become our culture. But the point is that the failure rate of startups is very high. And as Dr. Meena Mishra was telling, that fear of failure. So somehow we have to set the fear of failure, and fear of failure can be set by getting the knowledge of the field. So I like to cover, since one of the key points which I want to make here, that the role of academic institutions and universities have to play a major role in developing the startup and the entrepreneurial culture, which will lead to employment, and we can become from job seekers to job providers. And some of the examples which I like to give, that as earlier also mentioned, the Silicon Valley. Leading universities in Silicon Valley are 3 universities: University of California at Berkeley, Stanford, and the University of California at San Francisco. They have shaped the evolution of Silicon Valley. The publicly available literature survey shows that these universities have adopted the 4-point approach. I'm telling this because I want to foster this in our universities also. Fostering entrepreneurship education through the creation of new programs, competition and activities, even in non-entrepreneurial courses where we think that entrepreneurship is very, very difficult. And in multidisciplinary contexts. Commercialization of science and technology through entrepreneurs, connecting universities and their communities, staff, students, alumni with investors, and creating advanced infrastructures for translational research that may be expected to become even more closely linked to incubation and accelerator programs. Getting the valley, there is a valley of death in the initial stages of startups. So that we have to cross. So you're getting the valley of death between the identification and commercialization of useful findings. Role of academic institutions in Indian scenario. So what is our Indian scenario? Startups are crucial to economic growth because they create jobs, which lead to lower unemployment rates, which in turn signifies a more developed economy. India today has more than 2 lakh DPIIT recognized startups. And as per publicly available literature, leading academic institutions who have shaped the Indian startup ecosystem are IITs, followed by IIMs, ISB, and BITS Pilani. IIT Madras has set up Center to study Indian startup ecosystem, and India has many well-known startups coming from the higher educational institutes that include CISC, Atomberg, then there are many examples. So what is the way forward for this university or universities like this? So the question is that how Stanford, University of California at Berkeley, and University of California San Francisco have helped in evolving an entrepreneurial ecosystem in Silicon Valley. Can Indian universities strive to create the same impact in their geographical regions? Like this Chaudhary Charan Singh University, Meerut, is situated at a place where Noida, Greater Noida, Ghaziabad, industrial areas, and even the capital, Delhi itself, Gurgaon, they are all close to it. Can we do something that this university becomes the epicenter for creating an ecosystem like Silicon Valley in this geographical area. So my take on this is that a 4-point this thing which I believe can help in our work in our Indian environment is that improvised curriculum to develop an entrepreneurial mindset amongst the students. The first and foremost thing is to developing a growth mindset or entrepreneurial mindset. That fear of failure should not be there. Discover to uncover innovation challenges. So this kind of activity challenges can help in developing the, can be included in the curriculum to develop an entrepreneurial mindset. Then motivate students to incubate instead of seeking jobs. I believe that definitely incubator will be there in this university, and enhance the capacity of existing incubators. Can we have 5,000 startups in one incubator? That kind of scale. Then seek funding through government schemes, private ventures, by establishing government industry connect. That connect has to be established for funding, whether it is from government or whether it is from public sector or from private. So if we can do this, then the university can play a major role in converting the knowledge being generated in this university to wealth. And then that is one solution to mitigate unemployment. So knowledge, as far as I understand, it involves curiosity, creativity, innovation, and I add technopreneurship. The entrepreneurship based on the technology innovation. If we create this, then through startups we can generate wealth. So knowledge to wealth, and universities can become the torch bearers for that. The knowledge is being generated in this university. Can we convert it to wealth? And if we this, then we'll definitely be able to achieve our aim of Atmanirbhar Bharat. And why Atmanirbhar Bharat? Why can't we have Sarva Pratham Bharat also, first in the world? Can this physics department can have one pioneering research, which it seems infeasible, but actually it is not. Somebody has to take courage and do it. So, and I can tell you that for fostering certain kinds of ecosystem, one success is required. If somebody can develop a perovskite or synthetic material or a substitute of a rare earth material, one success is required, and one success in a fundamental sciences will lead to I don't know, billion or trillion dollar company. So, and one success will have a cascading effect, and so many successes will come. So first step has to be done. That will require efforts, and this is my expectation from this conference. I request all participants to participate actively, and the deliberations which is going to happen here, I can tell you these are the founder blocks for shaping the shape of this nation, both in civilian and defense military domains. So let us make our country technologically more advanced, economically wealthier, and militarily stronger. Thank you. Jai Hind, Jai Bharat.
We are truly grateful to you, sir, for your enlightening address and for gracing the event with your presence. Your word have deeply inspired us all. So carrying the same spirit of inspiration, I now have the honor of inviting Honorable Vice Chancellor Ma'am to grace the gathering with her presidential address.
थैंक यू कविता, आप सभी को सादर नमन करते हैं. Respected Chief Guest, Dr. Parimal Kumar, outstanding scientist and scientific advisor to the Chief of Integrated Defense Staff, Ministry of Defense, Government of India, a distinguished DRDO leader advancing indigenous defense technology under the Atmanirbhar Bharat initiative, and fostering innovation through collaboration with high-tech startups. So we are deeply honored to welcome you and to have you here. Your visionary contributions continue to strengthen India's self-reliance and technological excellence in the defense sector. आपका स्वागत, वंदन, अभिनंदन. I'm honored to welcome Dr. Meena Mishra, Director Solid State Physics Laboratory, New Delhi. Dr. Vipin Shukla ji, Head Department of Scientific and Industrial Research, DSIR, New Delhi. Eminent scientists whose leadership and contributions have greatly advanced India's scientific and technological progress. I am grateful, Madam, to Dr. Meena and Dr. Vipin Shukla ji, that we are really honored to have you here with us. Dr. Devshish from United Kingdoms, our ex-Pro Vice Chancellor, Mridul Gupta ji, Birpal ji, Anil Malik ji, eminent speakers, a list of eminent speakers from IITs and IITs, central universities and universities, esteemed colleagues, delegates, students and friends. It is with immense pleasure and pride that I extend a heartfelt welcome to all the participants, national and international, to this very important event, International Conference on Photonics and Emerging Materials for Futuristic Technology, hosted by Physics Department of our university. This event is a testament of our university's unwavering commitment for the advancement of science. It illustrates the tireless synergy, academic ambition, and scientific spirit to foster transformative research for the benefit of society and industry. This university stands proudly on the legacy of fostering academic excellence and nurturing research. आपने बीरपाल जी को सुना होगा कि यहाँ पे जो रैंकिंग्स हैं, वो रैंकिंग्स इस विश्वविद्यालय के टीचर्स, स्टूडेंट्स के वजह से ये रैंकिंग है, और we are very proud of our teachers and our students. As has been told by him, that we have Times Higher Education Ranking, NIRF, QS, and we have secured a prominent place in patents and publications, affirming our position as a leading hub for higher education in India. This is for the young minds, those who are sitting here, to understand. आज आप जहाँ पर बैठे हैं, आपको ये समझना है, जिस गैदरिंग में आप बैठे हैं, ये आसानी से नहीं मिलती है. अगर आज आप यहाँ से कुछ सीख के इनसे जाएंगे, तो जीवन में ज़रूर बहुत कुछ कर लेंगे. अभी मैडम ने बताया कि आपको फियरलेस होना है. सर ने बताया यूनिकॉर्न्स क्या होते हैं. सर ने हमको परिमल जी ने बताया कि आपको एंटरप्रेन्योरशिप को कैसे एक्सटेंड करना है. और सबसे ज़्यादा मलिक साहब ने बताया कि कौन कौन से स्पीकर्स हैं, कहाँ से आए. आपको मालूम है, जब हम लोग स्कॉलर्स हुआ करते थे, हम अभी सर को यही कह रहे थे कि सब बच्चे खड़े हैं, क्या ये स्टेप्स बनी, इस पे नहीं बैठ सकते. हम लोग तो ज़मीन पे बैठ जाते थे, पत्थर की पट्टिया पे बैठ जाते थे अगर कोई टीचर बोल रहा होता था. और अगर कोई बाहर से टीचर आया होता था, उस वक्त इतनी परमिशन नहीं होती थी हम लोगों को कि हम लोग उनसे डायरेक्टली बात कर सकें. तो हम लोग समय ढूंढते थे और बोलते थे कि हम सर 1 मिनट आप हमसे बात कर लीजिए, क्या हम आपके लैब में आ सकते हैं, क्या हम आपके लैब को देख सकते हैं. आज आपके पास सब कुछ है, लोग हैं, लैब है, मोबाइल है, गूगल है, आपके पास चैट जीपीटी है, आपके पास रिव्यू ऑफ लिटरेचर लिखने के लिए 3 घंटे हैं, जो हम लोग को 3 साल मिलते थे. उसके बाद भी अगर आप एडवांटेज ना ले सकें, आप सीरियस ना हो सके, आप सोच नहीं सकते जो लोग आज यहाँ पर हैं आपको क्या दे सकते हैं. ये आपकी सेल्फ क्यूरियोसिटी होनी चाहिए, आपकी सोच होनी चाहिए. फिजिक्स पढ़ रहे हैं तो क्यों पढ़ रहे हैं, आप क्या कर सकते हैं फिजिक्स पढ़ के. तो दिस इज अ मैसेज फॉर यू कि आप 3 दिन, मैं बोलती हूँ इन लोग का माथा खाइए. सर ये कर रहे हो तो क्यों कर रहे हो, हमको कैसे जोड़ सकते हो, हमको ये बिल्कुल नहीं आता, हमको ये सिखा के जाओ. ये होना चाहिए आप लोगों का आज अप्रोच इस कॉन्फ्रेंस के लिए. तो मैं सबसे पहले आप लोगों से ये रिक्वेस्ट करूंगी कि ऐसा समय नहीं मिलता, ऐसे लोग नहीं मिलते जो आज आपके सामने बैठे हैं। तो मेरा हम्बल रिक्वेस्ट है आप लोगों से कि आप इस बात पे विशेष ध्यान दें। अब थोड़ा सा सब्जेक्ट के बारे में, आई एम ए लाइफ साइंटिस्ट। फिजिक्स से मुझे हमेशा बहुत डर रहा, फिजिक्स और केमिस्ट्री से मैं बहुत डरती थी, इसलिए मैंने zoology, बॉटनी में एडमिशन लेने की कोशिश की। एंड आज भी ये फिजिक्स के जाइंट्स के सामने थोड़ा मुश्किल तो है ही, फिर भी मैं अपनी बात थोड़ा सा रखना चाहूँगी आपके सामने। We all understand this 21st century is the century of photon. In this contemporary era, photonics and advanced material science represent epicenter of innovation, promising transformative impact on industries ranging from telecommunications to healthcare, energy, defense, SDG goals, and artificial intelligence. The rapid evolution in these areas redefines the boundaries of what is possible, opening doors for strategic solutions and sustainable growth. Thus, the theme of this conference is very relevant, focusing collective attention on the applications of emerging technologies for a better tomorrow. And for this, I congratulate the entire team of Physics Department. We all know India pursues a vision of Atmanirbhar Bharat and digital transformation. Research in photonics and advanced materials is critical. Universities must take the lead in providing not only knowledge but also solutions to the real world challenges, starting from fundamental research to technology transfer and entrepreneurial ventures. So let us leverage this platform to spark innovation, initiate collaborative projects, and lay the groundwork for sustainable development. Solar cells and ultra-fast medical diagnostics. So at the heart of these innovations, the materials with tailored optical properties like semiconductors, nanostructured polymers, and layered crystals. These new materials can enhance our device performance, efficiency, and they can open doors for applications in various areas for research. I understand that every breakthrough there are challenges but more opportunities. Researchers must address issues of scalability, reproducibility, and integration to bring emerging materials from the lab to real-life solutions. The future lies in interdisciplinary collaboration and interdisciplinary research. For students, if we need to explore what can be the areas to work, so for me, like I thought some integrated photonic circuits and chips, they are expected to transform telecommunication, computing, and sensing, leveraging advanced semiconductor platforms for new fabrication methods. If we talk of quantum photonics and nanophotonics, they can drive breakthroughs in quantum computing, secure communications, and ultra-sensitive detectors, which we seriously need in our country. Homemade, make in India. Next generation materials including 2D materials, metamaterials, and smart composites. They can enable to innovate devices and expanded applications in electronics, energy, and healthcare. And if I talk of life sciences and medical sciences, photonics can enable high resolution imaging and non-invasive diagnostics that can improve disease detection and disease monitoring. Lab-on-chip biosensors powered by photonics can allow rapid and precise testing for health conditions. आप देख रहे हैं ना कितनी बीमारियां हो रही हैं, हर घर में बीमारी है। तो हम इतने तो अवेयर हों कि हम अर्ली डायग्नोसिस टेक्नोलॉजी की तरफ बढ़ें. Smart biomaterials support regenerative medicine, tissue engineering, controlled drug delivery and targeted therapies. हम फोटोनिक्स से इस पे काम कर सकते हैं जिसकी बहुत ज़रूरत है. Of course, AI integration with photonic technologies enables automated, personalized diagnostics and health monitoring. So this is what I thought this conference can teach to the students, and they can have with an open mind discussions for these areas. These areas will definitely and collectively represent many focal points for academic and industrial research, promising transformative impact across technology and society. I believe participation of renowned scientists and experts from across the globe fills us with pride and enthusiasm. Such intellectual congregation accelerates knowledge exchange, exposes young professionals to frontier research, and stimulates global collaboration. It is through forums like this, new ideas are born and lasting partnerships are forged. I extend a warm gratitude to all keynote speakers, session chairs, paper presenters, delegates for sharing your wisdom, expertise, and research. My special thanks to the organizing committee, which is led by the entire Department of Physics, for their untiring efforts, meticulous planning, and commitment in bringing this conference under the vision of scientific excellence. We actively encourage curiosity, critical thinking, and ethical research to the young researchers and students. Let this conference inspire you to dream boldly, question rigorously, and innovate fearlessly. Let us together strive to address the grand challenges of our society by harnessing the power of science and technology. Remember, only power that exists through entire globe is the power of knowledge. कोई position नहीं, कुछ भी नहीं है, सिर्फ एक position है, वो है power of knowledge. आप लोगों को वही बनना चाहिए. Let us embrace the future powered by photonics and advanced materials as we strive to create smarter, safer, and more sustainable society. I look forward to vibrant discussions, new collaborations, and the generation of knowledge that will benefit us university, the region, and the globe. I wish you a grand success. Jai Hind, Jai Bharat.
We are deeply grateful to you, ma'am, for your inspiring presidential address. Your vision and words of wisdom have truly set a positive tone for the conference. So as we come closer to the end of inaugural ceremony of PEMFT-2025, I would like to invite the organizing secretary, Dr. Neeraj Pawar, to propose the vote of thanks.
Thank you, madam. Dignitaries on the dais, chief guest of the inaugural function of this conference PEMFT-2025, Dr. Parimal Kumar ji, outstanding scientist, scientific advisor to Chief of Integrated Staff, Headquarter Integrated Defense Staff, Ministry of Defense, New Delhi. Distinguished guests, Dr. Vipin Chandra Shukla ji, Scientist G and Head, Department of Scientific and Industrial Research, DSIR, New Delhi. Dr. Meena Mishra, Madam, Director, Solid State Physics Laboratory, DRDO, New Delhi. Professor M.K. Gupta ji, Senior Professor, Chaudhary Charan Singh University, Meerut. Professor Birpal Singh ji, Director, Research and Development, Chaudhary Charan Singh University, Meerut. Professor Anil Kumar Malik ji, Convener and Head of the Physics Department, Chaudhary Charan Singh University, Meerut. Dr. Adroja ji from United Kingdom. Of the dais, Registrar Sir, Dr. Anil Kumar Yadav, Deans of various faculty head of the departments, faculty members, invited speakers from India and abroad, respected delegates, dear participants, students and media persons, sabhi ko mera pranam. On behalf of the organizing committee of this conference, it is indeed an honor and great privilege for me to extend my heartfelt gratitude at the conclusion of this inaugural ceremony of the International Conference on Photonics and Emerging Materials for Futuristic Technology 2025. First and foremost, I would like to express my deepest appreciation to our chief guest, Dr. Parimal Kumar ji, outstanding scientist, scientific advisor to Chief of Integrated Defense Staff, Ministry of Defense, New Delhi, for gracing this important occasion of this conference, and with your valuable address like career opportunities in physics and use of photonics and material science in the field of defense. We are also thankful to our distinguished guests, Dr. Vipin Chandra Shukla sir, who heads the DSIR, for sharing information of what activities DSIR is doing. We are also thankful to another distinguished guest, Dr. Meena Mishra madam, who is director of SSPL New Delhi, for sharing information to the participants about forces and about the utility and applications of semiconductor in the advancement of science and technology. I would also like to extend my sincere thanks to our Honorable Vice Chancellor Madam for an enlightening address and continuous support in promoting scientific activities at our universities. I also want to thank you, ma'am, for your outstanding leadership and tireless efforts in taking our university to new heights that have already been shared. All these achievements are testaments of the Honorable Vice Chancellor's ma'am's excellent leadership and her commitment in uplifting the scientific temperament of the university. We are thankful to you, ma'am, for guiding us with such a wisdom and inspiring leadership. A special note of gratitude to all our distinguished keynote speakers and invited speakers from India and abroad who have joined us online and offline from USA, Europe, UAE, South Korea, and within India from BRC Mumbai, CSIR laboratories, DRDOs, SSPL, IITs, central universities, CSIR laboratories for your active participation in this conference. So your participation enriches this conference, strengthens our commitment to cutting-edge research. So this conference has obtained funding from various agencies, so it is my duty to acknowledge them. I would like to thank our sponsoring organizations, Department of Scientific and Industrial Research, whose head is present here, Anusandhan National Research Foundation, ANRF New Delhi, Defense Research and Development Organizations, whose representatives are here, Board of Research in Nuclear Studies, BRNS, which comes under Department of Atomic Energy, our industrial partner IR Tech New Delhi, who partners Rigaku Japan, for their generous support, which have been instrumental in making this conference a reality. A heartfelt appreciation to the organizing committee, technical team and volunteers for their relentless efforts and dedication in ensuring the seamless execution of this event. Without your hard work behind the scene, this conference would not have been possible. I give my special thanks to all the academicians, researchers, participants for your enthusiasm and engagement. Your presence here today reflects the importance of collaborative efforts in shaping the future of material science and technology for making India Atmanirbhar, self-reliant and Viksit Bharat by 2047. Lastly, I would like to extend my gratitude to our Vice Chancellor Office, Registrar Office, Finance Office, Account Section, Engineering Section, Horticulture Section, all volunteers and all those who have contributed directly or indirectly to make this inaugural session a grand success. With this, I conclude my vote of thanks and look forward to fruitful discussions and meaningful collaborations in the upcoming parallel technical session. Thank you very much. Jai Hind, Jai Bharat.
Thank you, Dr. Pawar. So thanks to all of you for being here today, for your enthusiasm and for your commitment to advance on this incredible journey of learning and collaborations. Thank you once again, and I wish you all an enriching and engaging conference. So with this note, I request everybody present in the hall to please stand up at your respective places in the respect of Rashtragan. And after that, we will have a conference photograph at the Rangoli place, and then we will break for tea. So. जन गण मन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड़ उत्कल बंग विंध्य हिमाचल यमुना गंगा उच्छल जलधि तरंग तब शुभ नामे जागे तब शुभ आशीष मांगे गाहे तब जय गाथा जन गण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे. Thank you everyone. So I once again request everyone to please gather at the Rangoli place for the conference photograph.
Good afternoon, everybody. Introduction. And first of all, I would like to thank the organizer of the conference for giving us opportunity to present our work. The work is mainly, since we belong to defense organizations, so we are working for defense applications. So majority of my work will be related to all defense applications, but there are many civilian applications also of these compound semiconductors, and I'll try to include those also while presenting this. And majority of work we are doing at our place called Solid State Physics Laboratory, one of the premier laboratory of DRDO working on development of semiconductor materials and devices. So the outline of my talk is impact of wide bandgap semiconductors for modern day applications. And the outline of talk is, I'll start with the significance of wide bandgap semiconductors, why they are preferred, and then what is the landscape of wide bandgap semiconductor, what are the potential applications or where they are employed. And then the main four wide bandgap semiconductors are there, so I'll discuss each one of them. And then the one of the workhorse of wide bandgap semiconductor device technology is high electron mobility transistor. That is mainly based on gallium nitride technologies. I'll discuss that also. And then there is a new application coming up for power semiconductor electronics. Normally silicon technology is dominating for power switching, and then silicon carbide is coming up. But of late, because of the better properties of gallium nitride, it is replacing silicon, even silicon carbide, less than 1000 volt applications, and major target is electrical vehicle application. Then new semiconductor, because of its wider band gap, the diamond is coming up. So what are the potential applications? People are looking at diamond and how diamond is being utilized. And diamond is going to be the material of future. It is going to dominate the complete future applications for power electronics. Then there are certain laser diodes applications. Lasers are very much required for various defense and civilian applications, and we are also developing our own diodes. We are the only laboratory in India who is working on development of these diodes. So I'll briefly discuss that also. And then the gallium arsenide is also used for terahertz generation and detection. So how we are using the gallium arsenide for terahertz generation. I hope all of you would know that terahertz is coming up for imaging applications, for security imaging, homeland applications at the airport. They are now being deployed for detection of any concealed items, which otherwise is not possible. So what are wide bandgap semiconductor? Wide bandgap semiconductors are the semiconductor which have bandgap more than 1 electron volt. And why they are preferred? Because they work at higher temperature, they operate at higher voltages and higher frequency, and that results in more efficient, smaller, cheaper devices, as well as very high voltage capability power electronic devices. And as I told you that GaN-HEMT technology, this HEMT is basically a device which is an extension of MESFET. MESFET is a homojunction device, and HEMT is a heterojunction device. So heterojunction is a junction of two different bandgap semiconductor materials. And when you join two band gaps, one with higher band gap and other is with the lower band gap, and dope your higher band gap material when you join, because electrons are stable in lowest energy state, so they get transferred to the lower band gap material in a quantum well where there are no ionized impurities, so its mobility increases. So that is why it is called high electron mobility transistor, and they are preferred for high frequency applications. And gallium nitride being highly polarized material, so even it doesn't need the doping. Because of the spontaneous polarization, the carriers are generated in the quantum well to the tune of very, very high density, 2 into 10 to the power 13 or per centimeter square, which corresponds to a current of devices of more than 1 ampere per mm of gate width. So basically they are very high current density devices which we can fabricate operating at high frequencies, and that is why these gallium nitride devices are these days replacing all RF applications, be it radar, missile guidance, satellite communication. These devices are replacing the conventional gallium arsenide or other RF devices. So this is a very common slide. Normally we say that silicon is the material for 20th century, and silicon is still going very strong. And I don't think any other material is going to replace silicon till our lifetime, because silicon is so important. But there are many things which cannot be done with silicon. So you can see that these are the various applications which are not possible with silicon. So we need to have the compound semiconductor for this. And majority of these applications are for the defense and space applications. And in power electronics, as I told you, silicon carbide, gallium nitride, gallium oxide, diamond, they are preferred because of their wider band gap. So they can handle very high critical electric field, so they can operate at very high voltages. And for RF and high voltage application, gallium arsenide, indium phosphide, and gallium nitride. And if you compare silicon technology and compound semiconductor technology, why silicon technology is advanced? Silicon technology has advanced because of the process innovations. Newer and newer processes are developed. And today we are talking of a technology node of 2 nanometer. So how 2 nanometer is possible? Because of the advanced lithography process. But in compound semiconductor, the advancement have taken place because of the material innovation. Material is very, very critical. So material properties are exploited to get the better performance from the device. So if you look at the applications, compound semiconductor or wide bandgap semiconductors are everywhere. So it's in LIDAR, in data communication, then in radar, satellite communication, charging infrastructure, medical wearable electronics, wherever, or in photonic devices, lighting and display, everywhere these devices are utilized. And if you look at the evolution, the gallium arsenide initially it came because it is a direct bandgap semiconductor. So for any light emission, direct bandgap semiconductor is required. So initially it started with the development of gallium arsenide LEDs, then solar cell, and today we are talking of gallium arsenide micro LEDs or gallium arsenide VCSELs. It's a vertical cavity surface emitting laser diodes. They are very, very spectrally pure diodes emitting a single wavelength, which is used for many applications. Then if you talk of indium phosphide, again today we are talking of indium phosphide RF component. Indium phosphides are being now used for terahertz source applications at 0.3 terahertz. Then if you talk of gallium nitride, initially gallium nitride was used for developing white LED, and then now we are talking of gallium nitride microelectronic devices for RF as well as power electronics, and all blue-green LED laser diodes are now developed which are suitable for underwater communication for defense applications. Then silicon carbide, again, because of its higher thermal conductivity and wider band gap, it is used for very high voltage power semiconductor electronics. And these are advantages we have already discussed, so I'll skip that. And if you look at the growth of semiconductor industry, presently industry is growing at 7% compound annual growth rate. But look at the wide bandgap semiconductor or compound semiconductor, they are growing at 13% growth. So it's almost double of the normal growth rate because of their potential applications and use in defense and space applications. So if you look at RF GaN market, gallium nitride, as I told you, because it is possible to fabricate very high power and high frequency devices using gallium nitride. So all RF electronics is being now replaced by gallium nitride devices. And you can see the growth rate, almost 31% compound annual growth rate. So market is very, very high, and majority of applications are in military and space applications. And you can see that gallium nitride on silicon carbide is the best used device, and till 2030 it is projected to be used very widely for all defense and space applications, and later on newer devices or newer technologies will come. So that is why we also started at solid state physics laboratory this gallium nitride activity way back in 2008. And today we have our own technology, we have our own devices, and we are self-sufficient up to X band. And this project we have started to develop this technology while Government of India was purchasing Rafale radar, inbuilt radar on the fighter plane. And when we discussed the OPSEC technologies, they just refused to give this technology. So our management took a decision to develop this our own technology, and today we have our own devices up to X band, and we are now ready to supply for our indigenous Uttam radar. And this is one press brief which says that the devices which we have developed, space is big user for our devices. And this is a press brief from Government of India in 2022. You can see that the TR modules which are developed at Solid State Physics Laboratory through Gallium Arsenide Enabling Technology Center. We have one foundry placed in Hyderabad which is producing these MMICs, and continuously we are supplying these circuits developed within India for our space satellite missions. And you'll be glad to know that it is the only foundry in India which is space qualified. And this is the glimpse of the technology. You can see this is the complete wafer which we have processed. It is 3-inch gallium nitride wafer, and the substrate is silicon nitride, because gallium nitride has a disadvantage of not having any native substrate. So it requires a foreign substrate. Otherwise, silicon and gallium arsenide has always grown on their own substrate, but this is grown on silicon nitride being, silicon carbide, because silicon carbide lattice constant is almost close to gallium nitride, so lattice mismatch is minimum, so growth defects are very much less. And you can see this is the one device which can deliver power up to 130 watt in S band, and number of fingers are around 100. So this interdigitated configuration is preferred to have high current density, and the voltage operation is 50 volt. So these all devices earlier we were importing, but now we have our own technology, and the most important useful device out of this technology is monolithic microwave integrated circuit, in which a complete circuit is there in 5 mm by 5 mm. So you can see that this is one power amplifier delivering 30 watt of power. So it requires active component as a transistor, passive component, capacitor, inductor, and all these are integrated together to develop a circuit. So these are the circuits, and you can see that this is a interconnect, this is inductor, this is capacitor, this is resistor. All these are integrated in this, and these circuits are developed and used for the radar or missile guidance applications. This I'll skip. And the students who are into this high frequency electronics would know that a transistor is a 3-terminal device, source, drain, and gate, and the frequency performance depends on the gate length. How small is the gate length? To have higher frequency of operation, you need to have a minimum gate length. And for X band, the gate length which we are using is 250 nanometers, and to extend this frequency beyond X band, you need to go to 150 nanometer or 100 nanometer. So I hope all of you would understand how we develop this small geometry dimensions using a process called photolithography, in which UV light is used to print. But photolithography has got its own limitation of wavelength. Less than 0.5 micron we cannot print. So we have to go to electron beam lithography, where we can exploit the dual nature of electron. By accelerating voltage, I can reduce the wavelength of my electron beam and use that for printing. So we are using electron beam lithography, and this is the shape of the gate. It is called mushroom shape because I want to have a smaller footprint and wider head of the gate, so that it gives me smaller resistance, smaller capacitance. So these all technologies have been developed, and now I have a devices which can give me cutoff frequency up to 53 gigahertz, suitable for Ka-band applications. And then in conventional gallium nitride devices, aluminium gallium nitride is used as a wider band gap material, and gallium nitride is used as a lower band gap material. But if you replace this wider band gap material with some other better material like aluminum nitride or aluminum scandium nitride, where the spontaneous polarization is more. So because of this higher spontaneous polarization, I can have higher number of free carriers in quantum well, which enhances the current density. So I can have very high current density devices. And people have demonstrated the best results so far demonstrated with the cutoff frequency of 454 gigahertz with 25 nanometer of gate length. Similarly, aluminum and scandium nitride, you can see the current density is almost doubling or tripling. So by conventional heterostructure, I am getting 1E13, but by using a better spontaneous polarization material, I am able to enhance it 2 times, 3 times, so current density can be increased. And conventionally at X band, 8 to 12 gigahertz, the power density which is normally achieved is 5 watt per mm. But with this, we are able to achieve 8 to 10 watt per mm. So this is how there are different conventional techniques by which you can increase the performance of devices. But of late, for power applications, the gallium nitride is now picking up because of its better advantages in comparison to silicon carbide also. You can see that in any power switch, the two components are very important. How fast is the switching and how much is your R-on. So R-on basically decides your efficiency of the device. So whatever power you are putting at the input, you should be able to get maximum power at the output, and that is a function of R-on. And R-on is, you can see that for a same voltage, because the gallium nitride is having higher band gap even in comparison to silicon carbide. So for the same breakdown voltage application, I can have R-on 5.7 times less for gallium nitride. So because of this, it gives me better efficiency devices for switching also. So now gallium nitride is replacing silicon carbide for less than 1000 volt applications. Above 1000 volt, silicon carbide is always preferred because it has got a very high thermal conductivity. So this is the power switching landscape, and today you all are using mobile phones, and earlier when used to charge our mobile, it used to take almost a day or 2 days, but now it gets charged only in 20 minutes, 15 minutes. So that is thanks to gallium nitride technology. Because of higher current and high power switches, we are able to charge them. So almost you can see that less than 600 volt is completely now dominated by gallium nitride, and there is a competition between silicon carbide and gallium nitride for electrical vehicle market from 600 to 900 volt. And the who is going to win the competition is who is going to be economically viable, which both technologies are competitive, but whatever is cost effective will dominate the market, and above 900 or 1000 volt completely dominated by silicon carbide. This I'll skip. And then silicon carbide is very, very strategic material, and nobody is willing to give this technology to our country. So we have taken up a project at our place, and we now grow this crystal at our place and fabricate wafers of 4-inch. And the technique which is used is called physical vapor transport, and the complexity is that it requires a temperature of more than 2200 degrees centigrade. So very high temperature systems are there. So we have developed this technology. We have reactors at our place, and we are growing. This is a bowl which is a silicon carbide bowl of 20 mm, and then once this bowl is grown, and then the wafers are scribed from it, and then you can see this is what these are the 5 wafers. So these wafers are as good as anywhere in the world, and now we are using our own wafers for this device. So initially we were growing gallium nitride on imported substrates, but now these substrates have also been developed, and they are also used for power switching applications. And all of you who are following ISM, how many fabs India has set up in first phase in ISM? Fab only. Fabrication line. How many fabs they have set in ISM? Only 2. One Tata is developing at Dhulera, and other is in Odisha, which is the fab dedicated for silicon carbide devices. Then diamond, the band gap of diamond is, you can see that it is 5.4, and the breakdown field strength is almost 3 times of gallium nitride or silicon carbide. And then electron mobility, which is the essential quality for high frequency devices, is also very high. And thermal conductivity is best for the diamond. So diamond is now coming up as a best material for power semiconductor electronics, and people have already started using diamond. But in gallium nitride high frequency devices, diamond substrate is replacing silicon carbide. First we develop the complete device on silicon carbide and then remove silicon carbide substrate and put diamond substrate. Since diamond has got 3 to 4 times higher thermal conductivity, we can get enhancement in the performance by 3 to 4 times. So diamond FET MOSFETs are already in development phase. Diodes have been demonstrated with 10 kilovolt of breakdown. And even diamond is used for quantum sensing, because it has got nitrogen vacancies which can be leveraged, or which can be used for detection of the change in the magnetic field. So many groups in worldwide are already using diamond for magnetic sensing also.
Sir, last 5 minutes.
Okay, thank you. So this slide is just showing that how diamond, when replaces silicon carbide substrate, it can enhance the performance. Then coming to the laser diodes, as I told you that laser diode technology requires direct band gap semiconductor, and at SSPL we are using gallium arsenide and gallium nitride for development of these laser diodes. Gallium arsenide laser diodes are required for pumping application of direct energy weapon. So for weapon application we are using fiber lasers, but fiber laser requires a pumping source. So that source wavelength is 976 nanometer. When we pump the fiber laser by this diode, it emits in IR region, that is 1064 with high power. So have you heard of D4 system which was used in Mission Sindoor? So that diode fiber laser, it uses fiber laser of 10 kilowatt, which pumping source is solid state laser diodes, these semiconductor based. And then gallium nitride being direct band gap material, it emits the wavelength in the range of blue and green, that is 450 and 532. And in undersea, if you want to send a signal or communicate, the attenuation is minimum at these two wavelengths. So blue-green lasers are used for underwater application. So these lasers have already been developed at our place, and they are being supplied for different applications, but we are in the process of enhancing their performance in terms of power. And then coming to the last slide, the high frequency indium phosphide HEMT devices are preferred because for high frequency, mobility and saturation velocity are most critical parameters, and indium phosphide in indium phosphide, the electron effective mass is minimum. So it attains very high saturation velocity and very high mobility. So that is how they are the best devices for high frequency applications. And people have already demonstrated using 25 nanometer, 1.5 terahertz cutoff frequency or maximum frequency. So there is a thumb rule that your operating frequency should be 1/3 of your cutoff frequency. So when you have achieved 1.5 terahertz maximum frequency, you can operate these for 0.3 or 0.5 terahertz. So they are being explored for imaging applications as a terahertz source, and we are also working here, and initially we plan to develop 70 nanometer for 300 gigahertz, and as I told you that the frequency performance is the great function of your gate length, so you need to reduce the gate length. So we have electron beam lithography at our place, and we are developing this technology for terahertz applications. And many of the students, normally we take third-year students for internship and expose them to all these semiconductor technology tools. So if any one of you are interested, we are happy to welcome you there. Thank you very much.
Thank you, sir, for very nice lecture. and making us familiar with the Make in India kind of technology initiatives at SSPL. So session open for questions. One or two quick short questions.
बोलो जोर से बोलो.
Is-
Yeah. ISR radar is active electronically scanned radar, so it has to send a signal and then it has to detect the reflected signal. And PESA radar is passive, it is not emitting anything. It is just sensing the energy which is coming, reflecting, getting reflected from the aircraft. So when I am sending a signal, I am exposing my position also. So PESA radar is preferred for any covert applications where you don't want to show your position in the battlefield. So, but both has got their own advantages and disadvantages.
Okay.
But this gallium nitride technology is totally, Uttam radar is for ISA radars.
Any other question?
Sir, what is the process of DRDO internship for third year?
Internship you have to apply through your college from a letter from your principal or registrar and with your CV. And normally we give for third year student, it is 8 weeks training. So you can apply in the month of March, April, and you can come there for June, July or August. So that is the process, and normally we take 50 to 100 students every year.
Thank you, sir.
What kind of technology is used since the roughness is very less for the wafer?
Wafer, there are specialized techniques which are called epitaxial growth techniques. So there are two techniques. One is called molecular beam epitaxy, where we are doing atom by atom growth. Other is metallo-organic chemical vapor deposition. So both these are chemical vapor deposition techniques, but atom by atom growth. So normally the roughness which we achieve after growth is 0.3 to 0.4 nanometers.
Any other question? Sir, I have one small question. Yes. So, perovskite oxides like lithium niobate or barium titanate, high band gap. So, can we not use them?
Because their lattice constant is very important. Because the layer which I am growing over them, it should match with the lattice constant of the substrate. Then only I will have a non-defective growth. But defects are killers for the device. So lattice matching is important, where there are certain applications where lithium niobate we are using for surface acoustic wave detectors, where this lattice matching is not required.
Okay, okay. Thank you.
Yeah. Thank you.
Any moment? I think there is some moment. Organizer's side.
Yes.
Thank you. Thank you. Thank you.
Thank you, sir. So, the next speaker is, we have with us a senior professor, Professor Ravi Kumar. So, he has been group in charge, material science at IUSC, New Delhi for several years, and then heading at NIT Hamirpur, material science group. He has supervised 32 PhD students, you can realize, and large number of international publications, 368, edited around 12 books, and very high H index and I-10 index. H index 51 and I-10 index 220. So the topic of the discussion is some new mechanism for D0 electron systems, MO2, TiO2 and SNO2. You know, we need d electrons for magnetism in most of the cases. Welcome, sir.
There is a no either, there is a no zero empty d orbital, or there is a fully filled d orbitals or f orbitals, you cannot get the magnetic moment. In 2005 or around that, it has been observed that the nanomaterials or nanoparticles of the material which don't have a d electron, they are all are showing the room temperature ferromagnetism. The first paper came in hafnium oxide by Michael Coe, who is known as a father of magnetism, which is alive today. And after that, there was one paper by Sundareshan, who was my colleague at during my PhD time in Physical Review B. He has made so many nanoparticles and showed they all are ferromagnetic. And when these paper was read by my students, they all are doubting on those work. So my one advice to my student is that don't doubt on experimental work. Either you disprove it by performing experiment, or you can disprove by theoretically, until and unless sometime we always doubt our own experimentalist scientist, that is not correct. So then we thought that we should also look at whether these results are really, and if they are, then why we are seeing the magnetism. That was the project we have taken around 2005-2006 after reading those papers. So what is D0 magnetism? The observation of unexpected room temperature ferromagnetism in the semiconducting or insulating thin film or nanostructures of various material which have either d orbital empty or completely filled or partially filled. Now, flurry of reports we have seen which are giving some handshake explanations for those mechanisms, why D0 are showing the magnetism, like room temperature ferromagnetism through intrinsic oxygen vacancies. Some people are talking that they are defect or hole defects or the electron p-type defects, are possible due to the oxygen vacancies. So everyone was giving some or the another explanation, which is not satisfying any theoretical model, not satisfying any explanation was given by their paper, but somehow these are the new results, and under the umbrella of nano materials and nanotechnology, people used to get publication in good journals also. I can say the first paper is in Nature, and there are many physical review B papers or so papers are there. Our motivation is to study these kind of materials. As I told, my students were very angry because when you are a young man, you are always saying what I am doing, I am right, others are wrong. My understanding is very clear, others may be wrong. So my young student Ramjane Chaudhary, I call that as a young angry man, he came to me and told me, sir, what is this? I said, gentlemen, cool down. We should perform the experiment. So what we did, we took this project, the molybdenum dioxide, first project we have taken, and prepared the thin film using the pulse laser deposition. Second project, we used titanium oxide and tin oxide, making a film and then irradiating them with a high energy heavy ion. And then we started characterizing those kind of things, and that was the plan of our things. This is the crystal structure of molybdenum dioxide. This is the crystal structure of a rutile structure of titanium oxide and tin oxide. I am not going in detail because otherwise he will say time is less. Antas is a titanium oxide in another structure, and bruchite. The titanium oxide exists in three structures: rutile, antas, and bruchite. So now we deposit the thin films. I will not give all the details of the growth process because the standard, either you use a pulse laser deposition or you can use a RF sputtering techniques, magnetron RF sputtering techniques, which we have. Then here is I want to say the techniques which we want to use to understand the electronic structure of the material, because magnetism is a quantum phenomena which is defined on the electronic structure, and until and unless we are not studying the electronic structure, we cannot say what will be the reason behind the magnetism. So that is the reason my earlier papers, none of the person has bothered about studying the electronic structure, but they are jumping over their results without giving the right explanations of that. So that's why X-ray absorption spectroscopy is a element character specific. So you can study each and every element, under which environment that element in your material is lying, what kind of hybridization is occurring, and how the electronic behavior under crystal fields are being observed in these things. If I would have given a lecture in the department, I would have explained the technique fully. Now again, I'm just exposing you the X-ray absorption spectroscopy is an important technique, and earlier in our country we are unable to do that. Now at RRCAT we have a Indus 1 and Indus 2 where we can also perform. And when I was doing that kind of study, at that time these two synchrotrons, Indus 1 and Indus 2, was not operational. I have to do these measurements in France, Grenoble, and PAL, Korea, Pohang Accelerator Lab. And then there is a X-ray linear dichroism. X-ray linear dichroism is that again you will have a polarization in a horizontal plane polarization beam and vertical plane polarization beam. and that will tell us about the orbital anisotropy of the material. Then XMCD, X-ray magnetic circular dichroism, is again giving you the at individual site of how the spins are playing a role, and spin and orbital couplings are playing a role in those kind of materials. So there are various models also to understand that. I am skipping that things here. And spin orbital magnetic orbital moment, X-ray magnetic circular dichroism is a d orbital occupation, spin moment, orbital moment, how when you are performing those kind of right-handed circularly polarized light and left-handedly circularly polarized light, and how the absorption, which is depends upon their spin orbital coupling, is affected in that case. Now, these are the techniques we have used, which people are not bothering when they talk about the magnetism in those material which don't have the d orbital or f orbital and those kind of things. So for that, we prepared molybdenum dioxide, and you see these are the highly epitaxial. Just now my previous speaker was talking about the epitaxial growth, and we are having a highly C-axis oriented and epitaxially growth of the molybdenum dioxide film on a sapphire. So when you take the magnetism, it is showing a very nice ferromagnetic behavior. So it means that system don't have any d electron, and it is still showing the ferromagnetism. So what my earlier colleague was talking, it is right or wrong, I cannot say now. But we also observed. One way to stop this project, okay, I have also got the room temperature ferromagnetism. Very happy you published your paper. Otherwise, you have to do why it is ferromagnetism. So for that, we went to the X-ray absorption spectroscopy study, where we can perform the elemental specific techniques, and one can doubt that the magnetism is coming from any kind of magnetic impurity in your material. I can also doubt also in the earlier paper they must have a magnetic impurity. So we did this. First we scanned our material with all possible characteristics, sites like iron, cobalt, nickel, and so if there is any impurity, we can see through X-ray absorption spectroscopy. So those kind of L32 edges we have done, as well as the K edges experiments we have performed, because in a PAL lab, I have developed 2 beam lines which my students generally used to operate, and now I have stopped going there, but still some of postdoctoral fellow of my group and other groups are using those techniques. And then we thought, who will be in this molybdenum oxide? You can think that only the molybdenum is a site which will be magnetic, where the spin moment and orbital moment and total angular magnetic moment are present there. But we did the XMCD experiment. There is a very feeble signal. Even after expanding 20 times, the signal is 0.05 of the XMCD signal. So it means that the molybdenum is not responsible for the magnetism. From where the magnetism is coming? Then we did the oxygen KH. Friends, it was the first time of my surprise that oxygen is giving me very nice XMCD signal. Why oxygen is giving me a signal? Why the metal which is responsible for the magnetism is not giving a signal? Then we thought it is something different. So what is something different? We designed the experiment for X-ray linear dichroism. X-ray linear dichroism is that you have a horizontal plane, you have a vertical plane. And what is the absorption in that? That will depend how the orbitals are oriented. What is the density of state in a parallel plane and in a perpendicular plane? So you can monitor whether it is an anisotropic, and if the density of states are anisotropic, and the difference in a density of state in two directions giving me the magnetic moment. So that's why we performed this experiment of XLD, and we found a very nice signal which indicates that it's a orbital anisotropy which is responsible, not a defect, nothing. Why this is happening? When you have a nanoparticle of any oxide materials, we all know that surface to volume ratio is very high. And when the surface to volume ratio is high, you have a two-dimensional network. And there is a lot of strain and introducing an anisotropy in orbital. And that anisotropy orbital, maybe sometime it is not coming because they cancel each other in a nanoparticle. And when I have a epitaxial ultra-thin film grown, I can revive that kind of a orbital anisotropy to understand the mechanism of that. So we have not only done the experiment, we also performed the theoretical analysis of that. If there is a orbital anisotropy, can I see the magnetism in the materials or not? So our theory as well as our experimental results are supporting each other. Why it's not moving? भैया just slide नहीं चल रही. So in summary, I can say in this particular system, then I thought it is in a molybdenum one material. Can I see some kind of similar result to support my theoretical as well as my experimental observation in another materials or also or not? Then we have titanium oxide and tin oxide, which are a lot, if somebody can be a technology person, he can say many technological applications are there. And there again, after irradiation with swift heavy ion, आपके बगल में दिल्ली में इंटर यूनिवर्सिटी एक्सेलरेटर सेंटर है, where I have spent more than 13 years of my services. We can transform the structural transformation from one phase to another phase. Here you can see one can have a untouched thin film and titanium oxide to rutile and bruchite phases are also there. And okay, so these are the analysis we have done with the radiation. Then we again did the oxygen KH and studied the XMCD at oxygen KH and found a very good signal. And titanium site, no signal is observed. And here XLD signal is also good. So any kind of oxide material you take, you will have a very nice orbital anisotropy in those kind of a system, which supports my theoretical background.
Sir, last 5 minutes.
Yes, I am going to finish. So lot many experiment. There again, their room temperature ferromagnetism is also there, and you have a XLD signal at the oxygen KH, and the orbital anisotropy we have proved. If you take a further even tin oxide, the similar case we have seen in a tin oxide also, and one can study the XLD signal also there. The orbital anisotropy is very well. So in summary, I can say the D0 magnetism, we have not only experimentally proved that, we have theoretically also proved that the basic responsibility when you make a bulk material, you cannot get the orbital anisotropy because they are cancelling each other and very uniform environment you have. When you make a nanoparticles, as I told you, there is a surface to volume ratio is very large, and you have a 2D effect and a highly strained surface. So sometimes your nanomaterials are giving you ferromagnetism, sometimes don't they cancel each other also because they are randomly oriented and random distribution of the magnetic moment. But when you make an isotropic thin film, you retain the orbital, the epitaxial thin film, you retain the orbital anisotropy in your system, which will give you the magnetism, which we have proved not only in one system, 3 systems I have proved, and then I left the game for the others to do research on other material. Otherwise सारा कुछ हम कर लेंगे तो site हमें कौन करेगा. So these papers have more than 250 citations, and because here we have given the fundamental mechanism for the magnetism also, which is from the conventional magnetism, it is a different kind of a magnetism. So many of my senior colleagues like Michael Coy met me in Trinity. He told me why my student I could not think. I say Pauli's exclusion principle. No two mind have same quantum numbers. No two electrons have the same quantum numbers. That's what a Pauli's exclusion. Same way, no two scientists have the same thought process. You have some thought process, I have another thought process. Whose thought process will click, that matters a lot. And thank you very much for your kind attention. Any question, any doubt? Because my excitement here was to tell the young people that there is a new mechanism of magnetism we have given.
Thank you, sir, for a very nice lecture. Questions?
Anything you will get. I have shown, today I have shown you. Yes.
You made it all in the thin film, sir.
Madam, nanostructure I cannot control. Guarantee. See, when I am giving the XLD is nothing. It's a vertical plane polarized light and a horizontal plane polarized light. And if my material I cannot orient on those kind of things, you must have, I'll show you the geometry of my experiment of XLD in one of the slides. So that in nanoparticle I cannot maintain that.
But the result shows it as you say that when experiments cannot be wrong. Yeah.
See, I am not saying nanoparticles are wrong, but in nanoparticle, your signal may be cancelled out by the distribution sometime. And in some time you may get a strong signal. But here, to prove that, my theory, I have to go with a thin film. Nanoparticle को मैं horizontal plane and vertical plane polarized light में नहीं कर सकता. That was the reason. Any other question, please? हाँ जी, दरोजा जी. See here the signal is in this case is a weak, but in titanium oxide the signal is very good because the film is here I am say it's a Bohr magnetron is not like your rare earth those kind of a system. We will try, sir. See, question is that in Newton diffraction, again the volume of the sample required is large. मैंने कौशिक से बात की थी तब कि कौशिक
No, not in that lab, but in the ICC we have the new instrument.
If you offer me a time, I can definitely do. किसका दिल नहीं करता इंग्लैंड जाने को जहाँ वहाँ जाके बड़े-बड़े एक्सपेरिमेंट करने को? I am happy if you can offer me. We will prove that also. Yes. That's what I have shown here. Oxygen is coming. Similar thing. Question, Adroja ji, question is this. You can do either one system. That's why I took 3 systems. After that, let the people do another system. The fundamental philosophy will not change. Okay, Newton diffraction, yes, we can also try those kind of experiment. We are old friend. We met after 40 years. का विछोड़े के बाद हम कल रात को मिले हैं, तो दोबारा हम फिर अपनी collaboration कर सकते हैं. क्यों नहीं कर सकते? Any other question, please?
One last question.
Yes, young man.
I have a question that how much it can help to develop any business for the
Gentlemen, there are 2 aspects of science. One aspect is a fundamental physics. Another aspect is a application. Today, when we talk about the quantum computation and quantum mission and qubits, we have to do in a ultra thin films. So there one can, these kind of experiments and these kind of philosophies are very useful for the quantum missions and quantum experiments. That's what I can say. But right now, my purpose is to give you the fundamentals of magnetism, which is totally not matching with the conventional theories.
Sir, there is one scientist named Abir Sarkar in Indian National Nanoscience.
He is also
Yeah.
my very close friend, and I think Neeraj know, इन दोनों को मैंने इंटरव्यू लेके सेंट्रल यूनिवर्सिटी में सिलेक्ट किया था, and ये मेरी वजह से ये एकेडमिक्स में बैठे हुए हैं.
Sir. Sir, he is doing a job with nanoscience, with a computational field.
He's a very good DFT person.
Yeah, yes, sir. So, he is running their own laboratory. So they provide internships. If I want to join them, I require a lot of work to join there. If any chance to work with you, how any person can work with?
See, I am a simple master, टीचर आदमी हूँ. मैं इंटर्नशिप नहीं कराता हूँ लोगों को. मैं PhD करवाता हूँ, अंडर ग्रेजुएट स्टूडेंट को पढ़ाता हूँ, पोस्ट ग्रेजुएट स्टूडेंट को पढ़ाता हूँ. Those research institutions, they have only, we have lot much work on teaching and another our research also. So internship, it is better you do with a research laboratory like INST or another CSIU lab or DRDO labs, where you can learn more in an internship. Here I will teach you quantum mechanics, which is boring for you. I will teach you solid state physics, which will be boring to you. Within a few weeks, neither you can understand the quantum mechanics nor solid state physics. Devices I am not making. So what you will do with the internship with me? Better you do internship in a right person.
Younger people.
Not younger people, they have the mandate of the devices. And secondly, gentlemen, nowadays there is a fashion of startup, patent, incubation, devices, this thing. Until and unless we don't do the basic sciences, all the technology is emerging from the understanding of basic sciences, which our young generation or even some leaders of our country, scientific leaders, they have spoiled that culture. To understand the basic, कौवा चला हंस की चाल अपनी भी खो बैठा. ना हम बेसिक जानते हैं, ना हम टेक्नोलॉजी जानेंगे, और टेक्नोलॉजी से ही बेसिक आता है.
Yes, sir.
I have a patent on bolometers, magnetic sensors, from my fundamental study of CMR materials. Ram and myself has done those kind of things. First we understood the basic sciences of the CMR materials, then we made the devices and got a patent of that. But if I will run behind the patent, ना साइंस रहेगी ना पेटेंट रहेगा. और पेटेंट भी वो रहेगा जो लोग पेटेंट की बात करते हैं ज्यादा. मैं उनको एक स्टोरी सुनाता हूँ. मेरी डेफिनेशन ऑफ पेटेंट इज दैट हम एक बंजर जमीन रेगिस्तान में खरीदते हैं जहां ना बरसात होती है ना लैंड उपजाऊ है. जे इच्छा करते हैं कभी वहां प्रभु कृपा होगी, बरसात होगी, गेहूं उगेगा, रोटी खाएंगे. ना बरसात होगी, ना गेहूं उगेगा, ना रोटी खाएंगे. वो पेटेंट डाई ऑफ हो जाएगा. कुछ लोग कहते हैं कि मेरी लैब में 75 पेटेंट हैं. I will say, how many you have commercialized? None of them is commercialized. And ना तो साइंस कर रहे हैं, पेटेंट की तरफ से बेईमानी कर रहे हैं. बदतमीजी तो नहीं कह सकता, बेईमानी कर रहे हैं. तो इसलिए understand the fundamental science. Outcome of fundamental science is a technology. So it is a request to all the physicists, concentrate on your subject rather than running behind the.
So you have lots of ideas for discussion during lunch time with sir. Thank you, sir, for very nice lecture. So we are running out of time, definitely. So next speaker is Dr. Vasundhara Mutta. So welcome, madam. She has lots of experience in different research labs, nationally, internationally, She is currently at senior scientist at CSIR lab, IICT Hyderabad. And she has published lots of paper, around 130 publications in international journals, completed several sponsored R&D projects, lots of invited talks, and member of several academies. So welcome, madam. She will be talking about thermoelectric materials for cooling applications. It's over to you, madam.
Am I audible? Yes, now? Thank you very much, sir, for your introduction, and thank you very much for the previous talk was quite interesting. Sir, it is very much agreed that today's science is tomorrow's engineering, and tomorrow's engineering is day after tomorrow's technology. So basic science, we need it, and government also understood after this COVID incidents, and they made their own things, because I come from a scientific laboratory, so that's just telling it. Thank you very much. And it's already, we are 1.5 hours nearly getting late, but I will try to make it very crisp, the talk. But I had to explain some of the fundamentals. So if you have any discussions, we can talk during the lunch time. So this is about the recent advances in the chalcogenide materials for the cooling technologies as a potential thermoelectric materials. So why recent, before going to that okay, it's good that 2 slides yesterday only. After I had my pre-conference talk, I understood that I had to include it. So this boy is raised that question regarding the internship, so this is the correct platform. So what is I mentioned? So CSR organization, it has been, before independence, 1942, this organization has been made with the intention that the main mission is that it should provide the scientific industrial research and development for the people for different applications, scientific and Council of Scientific and Industrial. So S stands here for 2 societal benefits also. So the target 2012, I joined in this organization when the thing it has come that when the societal application, we have to work on such a research areas which has to directly benefit the society. So at least if we cannot benefit all the people, at least 800 million people, I mean 800 people we should be making. So that's why they made CSR 800 the work. That work is related. So in that CSR 800 means we take the PhD scholars, out of that 1 coursework which is a 4 credit points which is based on the CSR 800. So 1 coursework, it should be directly associated to the societal applications, no matter what theory, what experimental you do. So they have to undergo that one. So that is one of the NARA it has made after 2012 the things. So CSR, other than fellowships and travel grants and sponsored projects, these 3 they project for the outsiders other than the CSR people, other than our internal the labs. So in 2010 this academy has started, which is a ACSR, which is a similar to that Homi Baba institution of this BRC, DAE, Academy of Scientific and Innovative Research, which is an institution of national importance. It's granted by Parliament of India, and till the date, the awarded degrees were 4,000, and in 2025 is not yet completed. So in the last year it was 831, and now as of now the registered candidates are 7,200 under different disciplines. So this is a CSR, it's a chain of 37 laboratories spread over across the country. Based upon its, each laboratory has a specialized for certain things, like we have in the southernmost one of the laboratories is CLRI, which is for the Leather Research Institution, and CRI Pilan, that's also electronics, CFTRI, which is a Food Research Institution, and in west to CSMCRA, which is a Salt and Marine Central Research Institution, and in North IIIM based upon the intensive integrated medicinal work. So each one has got its different expertise. Even we have in Bangalore, that is a NAL, which is one of the biggest laboratories with consisting around 1,000 to 1,200 scientists, which is the National Aeronautical Laboratories. I belong to the place where this is a ISCT. Initially, I worked in this extreme end of this country, which is an interdisciplinary laboratory at Trivandrum. Now I am working in ISCT, which is the Indian Institution of Chemical Technology. So how it is connected? It is all the labs has made of 5 clusters based on their expertise, like physical sciences, and this is mostly the chemical sciences, and amongst those the things, there will be a mission mode projects it goes on. That is the internal administration and the scientific it works. The aim and mission is it has to be societal, scientific and industrial. Industry component is very important to work on that one. What sir mentioned is that, but it has a mandatory course for us. So the total, the strength, it was initially nearly 10,000 scientists, but presently the entire staff is gone to down to nearly around 10,000. Even it has come down. Scientists 3,489 as of till the date with the other support. Then this ISCT, which is in Hyderabad, there's a located. One of the famous thing ISCT, if you do not remember, you understand during the vaccination, during the COVID time. So this laboratory has participated in making even small molecule, okay, during that time it was done. So if I say, then you will not be forgetting about the ISCT. And with presently we have a 489 staff with a 169 staff. This is the thing. And internship, we allow the PhD students and masters who come from every year, nearly 500 to 600 people. They come for the different academic industries to work as interns for their projects. So you can just approach that website and all. So now the work is coming about the top. This is about the CSR and what all the benefits you can take. Please take it up. So this work, today's thermoelectric effect, which is your +2 science, you heard about that one. If you create a voltage across the material, it will generate a temperature gradient across that, or vice versa. If you create a temperature gradient across the material, then it will generate the voltage. So this one, this effect, that is the thing. So you can convert your thermal energy into electrical, which can provide that refrigeration directly from the electrical energy. Now the question, this is the fundamental, but how this fundamental, it will be utilized for your practical applications. That is what the thing. So now the primary power generation and energy conversion, how big this role is likely to be in our society. I mean, what we are day-to-day life, we are using it. I mean, how much we need it. That is how big this role is likely. And it depends exclusively on how efficient these materials. See, later the technology, engineering part, it comes. The basic thing is the material, how much ability it has it. So without materials, the other two parts, it cannot come into the picture. So these materials are how to judge whether this material can get a good energy conversion. So to understand that one, there is a figure of merit of this material that's famously called as ZT, which you all know. I know the graduate students, you must be knowing because it is having the subject. So where ZT is a Seebeck coefficient, which you call as a thermoelectric power, and electrical conductivity and thermal conductivity with the temperature, and this top, which is, we call it as the numerator part, that is a power factor, and that this one is a thermal conductivity. And you know that there is a famous law, French law, what it says that all the good thermal conductors are, electrical conductors are good thermal conductors too. But here you need the opposite. So all these three are the complementary to each other. The problem is that you have to design such a material which may not be available in the naturally, all are this, what are the periodic table elements are there, cannot be. Every element has its own merits and its own demerits, which is not suitable to the other composition, other practical applications. So so we need to design the materials accordingly. So for a solid state device, this is the material property. This is the for a device making, you need to check about the electric efficiency, which is mentioned as a zeta, which is this equation which I'm not going to the intricacies, please, due to the lack of time. I need to wind up at least before 2. So this is what it gives the efficiency of the device. This is famously called as a Carnot efficiency, Carnot engine, how much it works. Now presently, do you have any idea that what is the efficiency we are able to use it? It's barely the practical applications are 10% of the efficiency. So how big this is, that one, if any theoreticians claim that it is 100%, how big gap is there to work? And in the refrigerations, these are the very fundamental, whether it is an ISRO or space related research, this thermoelectric efficiency materials are required. So now, what is the factors? All the 3 parameters, it's not in a once lifetime of the research cannot be possible. So there are the scientists, group of scientists who are working on, let us enhance this factor itself, because these 2 guys, it can be easy to control. Whereas if you talk about the thermal conductivity, that's going to be a completely different phenomenon, and you will end up with doing nothing else. So what it comes is that there is either you increase the numerator or you decrease the denominator to get the better efficiency. So these kind of things are, it is going on. So now for this criteria, what it is that that these metals, semiconductors and insulators. For a metals, this power factor value, it comes down like this. For insulator, this is increasing. Whereas the thermal conductivity is completely opposite. So the best thing is that somewhere else you have to find it out here in this area. Neither this nor that. I mean, it's not in a insulating region, not in a metal. So choose the materials which has the middle of that, so that it is easy to tune off based on your requirements. So this is the thing, semiconductor materials are the best, and there is a many band gap engineering we can do. So out of that, chalcosenides and semiconductors comes. There are semiconductors also, there are again things. One is a wide band gap and narrow band gap. So let us take it also. That's how the chalcosenides come into the picture. See, so the thermoelectric device efficiency in the present market, what it is showing is at a high from entire temperature. This I took it from some of the references. So what you see that when this 1% to 10% zeta T, which is a potential, and it shows the 40% of the efficiency at a higher temperature. So this is the availability with a wide range of materials. So that's why I put it the recent trends. So these are the thermoelectric materials known to the humankind. I mean, as of now, the people, whatever is searching, that is a lead based, and lead based due to, because of its certain obvious reasons, lead is avoided. But that is even though in certain cases it is not avoided, 18% of the thermoelectric materials are lead based. Then the bismuth telluride, even though this one is a 10% efficiency, which I had explained, that one it is in the industrial usage. Then this is the scenario which goes on. I mean, this is a percentage of the materials are there. And then this is up to last another 10 years it has to commit. This is is a plotting mistake. It is a 2024, the related. So these are the potential materials. See, zeta value 1 means it is 10%. Just in the previous slide which I have shown. So it has gone up to the 3 range the moment when you made either nano structures and super lattices, 2-dimensional, when you use a carbon nanotubes. So all these people have done with this one until the research it has come to the 2%, means it has gone to shown the efficiency 20%. But in a practical applications there is a limit how much is, see, when you do the applications there is a word you need about the economically viable and the production rate. So these are all the things, the limits. But this is the recent advances it happened in this area of that one, from 10% to up to the maximum 35% the material SNSE are showing. But now the question is, all these materials are not showing at a one particular temperature. So refrigeration, you need it at different applications. Some like in ISRO they need it at very lower temperatures, and room temperatures we need human beings to survive. We need room temperature, ACs and all. But at high temperatures too, they need it. So at different temperatures, this one figure which shows the information around the ZT values shows the performance and the values at a different temperature ranges. Please, just that must be noted down. Okay. So now, when you make it, I said that this is a thermoelectric material. You will see the numerous papers with having with a G. We got this much of a efficiency and all, but it is immaterial until and unless you make a device. So it is for to show only this material is a potential. Now to make the device, you need two legs. One is a P-type and N-type. Both the things are required. So when you choose a P-type semiconductor and N-type semiconductors, to again you can't use this material and this material as a P-type N-type leg, which is an irrelevance. So you need to choose a material which are showing at least some common particular temperatures, the nearest values. So that will give you the device. It works. So okay. So this is the difference. So this is the available P-type material. This is the available N-type material. So here you can see why we chosen here that the interest topic of chalcosenides, because this has a moderate values which can be clubbed together at a particular room temperature or anything else which we work. So in this work, this is the entire scenario, the chalcosenides I have chosen it. I will explain to you why it is that. Now when from thermoelectrics, when we moved from bulk to nanomaterials, how it has changed the scenarios, please just check it out. It has from initial value 0.03 to now ZT value greater than 2 in a silicon germanium the chips it has shown. So here there are two mechanisms which you can control it. One is in a bulk material there is a almost is a saturation it has reached. The reason is in the bulk material this alloy has a limit thermal conductivity. Thermal conductivity depends upon the mean free path. Mean free path means what? Yesterday some of you have attended the class is that electron which can travel with, I mean the average, you know that the definitions, let me not get into that. So here the mean free path is limited in the bulk, whereas in a nanomaterials, because of the huge surface to volume ratio, you have a plenty of options. I mean if you just wanted to will on that one. So here by nanostructuring you can the nanoscale reduction, because the K is possible to reduce that thermal conductivity, you can just make nanostructuring is a preferable. So now in this case the same the previous one only which I explained. So how do you, what is the strategies to improve this existing figure of merit to get the better materials is either you increase this portion or you decrease this portion. So this portion increases are related to mostly in the bulk values, and in the thermal conductivity is done by creating the defects, vacancies, or by nanostructuring. So let me, I'll just talk about these things only. Okay. So now all this is the recent advances and the fundamental and the properties I had explained you. Now the material which we have chosen is the chalcosenide, which I have shown that one, the 18% of that work is done on this work, and it is being used, useful material. So in this interesting structure, what it is a hexagonal structure with this top is lying this one, and here the importance of this crystal structure is the length. This one is very larger, you can elongate it. So this helps in reducing the thermal conductivity. So this material was chosen for that. So this is the basic crystal structure schematically we have drawn. So in this case, now let me tell you about the bismuth telluride, what the previous and what nanostructuring is helping. Bismuth tellurium is both are metalloids, intermetallics kind of a thing. So the best way of making the material is in the larger scale is the metallurgical routes, but you understand the limitations. Bismuth and tellurium, both the temperatures does not match. When you just once boiling, melting, because both are having a versatile materials. So if you do the mix up, there is a loss existing. So completely perfect stoichiometry is a real challenging in getting the bismuth telluride material. So what we have chosen here is to a chemical synthesis, and based on previous so many literatures we understood is that bismuth is at around for tellurium is a 440 and bismuth is a 260 degrees melting points. But we have chosen this material to get it growth under the environment of 100 boiling point of a water, so that there is a no scope of getting evaporation of anything, and we will get a perfect crystal structure which is as good as shown in the theoretical. So this is the challenging was done. One of my initial stages PhD student took it up, this work. So here we have done using some reflex method, where we have chosen the bismuth chloride and the tellurium powders using certain chemistry. If you will need, I will just explain you this thing. So this aqueous method, what is the novelty is here is that we have taken the bismuth chloride and tellurium powders. This entire reaction, it happened under the environment of a boiling water. Of course we had to use the surfactant and pH adjustment, those things we have done. But we made sure that while growing the crystals, the entire environment is not going below 100 Kelvin. So there is no scope at all to get the evaporation of the elements, individual elements. So in this case we have done, this is the initial thing we had to adjust. This is the parameters we worked it for different reaction times. Now we fixed it a particular normality of this one. So the reaction we let it happen from 1 hour to 36 hours. We had even gone to 64 hours also, but it was not needed. So different hours. It was a slow reaction mechanism. So continuously the person has to be monitored using. So we found the different bismuth telluride nanostructures using this one. So these are the crystal structures. So these are the parameters which is after lots of trials, after 2 years it is a success. So this one line I have mentioned here. See here bismuth tellurium, different structures are formed. And the hexagonal, which I said that on the most reliable structure for getting the low thermal conductivity is hexagonal. We got it for the 24 hours reaction time. So you see this from the morphology. Morphology also here and here the separate crystals are there, and this also we had explained why it happened, because it's a lower time it has formed, and then it is changing into the core shell kind of a structures. Then finally at 24 hours we got a well dispersed nanostructures, and then beyond that one again it started growing and it got agglomerated. So the critical time which has been taken is 24 hours. This is a pure basic work, because 24 hours reaction we do not expect for the practical applications, but of course that is also important based on the necessity and requirement. So now it's the thermoelectric properties, we have studied all the thing, and I will directly go to the figure of merit. That's what we have. You just see the figure of merit values which has come for this 1 hour and 24 hours reaction, and whereas all other things which is not that much of prominent, it is the highest value we got the figure of merit is for the 24 hours. So the reason is we had explained based on the morphology, where you remember for 1 hour and 24 hours of well defined structures we have got it, whereas in 24 hours time and 12 hours time, this is a mechanism where one you explain that suppose if you take it a hot end and cold end, how the wavelength of the phonons it just goes at. One is a long wavelength, and you can see that the electron interactions, whereas the bigger particle size the collision is very fast and you cannot get a better thermal conductivity. So that is the reasons which is just I explained you that you need a highest mean free path. So we got it for the 24 hour reaction. So the figure of merit, even though which I mentioned at 300, we got a 0.67, whereas a 1% is a theoretical value which I had explained. So from this point we understood is that we can get a better value using this synthesis. Then we fix that value, and what we have done, we have to use that whether this mechanism by making a 24 hour reaction, whether is it possible to enhance the GT value. Yes, we did it. Then what we have done it, see earlier we just explained it, 75 is the designed one. Then what we have done, we have increased the EDTA solution, the surfactant, and decreased also. So there is an option. So when you just make a thing in a very bigger volume, smaller volume, there is a limit. That also, even though theory mentioned, but experimentalist we have to mention it. So we worked on it. One is a before and another one. Then you see the changes. All the same mechanism we got it, but the crystal structure within the lesser time reduction. So all the things we got it for this one, even though this one we got for the 24 hours, then that too, that was not that much enhanced values, but for a highest concentration we got for the 12-hour reaction time. So this is the crystal structure we got it. So 12 hours reaction time we could reduce it with an enhanced ZT value, the outside. So this surfactant concentration, this of course facilitates the formation of the required desired bismuth telluride within a lesser time. So this is the one, and okay, a new pathway we got it for controlling the thermal conductivity in a just a perfect manner. So now what is that one? So see this, crystal structure is very well known. However, you see these dimensions, how it has plate kind of a structure we got. That is again same mechanism. We see this one, and you see from 0.67 to 20.75 value is increased. But because I said it has a 3 parameters, so other parameters have not controlled. However, the thermal conductivity, which is a 35% lesser than the existing one we got using this mechanism. Yeah. So this is it's a simple chemistry. It's a simple chemistry, but 5 years of hard work of one of my students. I'm just mentioning here. So what could be the reasons of this bismuth, and when we use a lesser concentration, higher concentration, and perfect concentrations? So when the volume is more, what's happening is that this surfactant is taking care of the bismuth ions, and it is not allowing to, it is allowing to growth it into the plate kind of a structure, and after that intermediate reaction it is getting formed with the tellurium. So that is the reasons of getting this kind of a crystal structures, and that is the reasons for getting the reduction of a thermal conductivity. So this is that chemistry has explained the materials. So this is the overall mechanism, reaction time. With reaction time and the values what we got it, in this case that is the best volume we got it, because we got the two-dimensional structures. Both for nanorods and okay, I'll just so this is the overall thermoelectric performance of bismuth tellurium nanostructures. In our work we got it. So the best one we got it using the value is a 0.75 near the room temperature for the highest value, and this is a comparison of our work with the recently reported or earlier. He is my student, Dr. Akshay. So what we got in this novelty of the work which we explained, it is a 37% reduction in the thermal conductivity and electrical conductivity enhanced by 2 times. The overall enhancement of the figure in this work is in the comparison to the present state of art of materials is a 15%. So then we expanded this to other materials also. Like as I mentioned, that one single developing, it does not make sense. You have to make a P-type. So we have used the P-type for this. We have added the antimony into that one. Then what we got is that from an N-type to P-type transition, we got it in this material. So that explain again that this one I wanted to skip that one, because if I need to explain, I have to explain Hugh's work. So the summary I'll just explain you. So what in this one we have used the individual elements below the melting point of the individual elements, so that the one enemy of this bismuth tellurium is the mixing of these two alloys. But that is the natures. These two elements are giving the best product, best thermoelectric power in that one. But the challenge is that how to make that alloy. So we use the temperature controlled, and apart from that we change the concentration of the surfactants and then volumes. So that control we got it one of the best material which is in comparison to the exist. This is the latest one. 2017 onwards the student has started, and recently it has completed. He completed. He's winded up his thesis of this very good piece of work. So we are successfully, we could make the material which is one of the oldest material. 1950s onwards it is there in the market. With an enhancement of a 37% efficiency, we could grow up that one. I'm sorry, very fast, but I had to be, because I know that you are young, hungry. This slot is very crucial. And after lunch also, even it is crucial. I know that one. So I just thank you.
Thank you very much for a nice presentation. Few questions, yeah.
Please. Yeah. Yeah. Sure.
So can you prepare the single crystalline nanostructures?
No, here single crystalline nanostructures, sir, you need to have a different setups. We do not have.
Can you give some example?
Like Brigadman, we have a floating zone techniques and all, but here in chemical synthesis also people have done, but it is not a single crystal, it is a bulk material.
Okay.
But even though bulk material, this bismuth tellurium was such an anisotropic, when we made the powders in plane and perpendicular, it has shown that anisotropy.
Can you show some oscillation kind of thing in this structures?
Which one, sir? Example?
Like Sobnikov deoscillations.
Sorry, I could not.
Sobnikov deoscillations.
No, I could not. I cannot show
in,
it.
In resistivity.
Resistivity, please. We just check the values and it's a metallic and semiconductor, non-metallic performance only we have shown. Yeah. Yes, this is the value. We got it.
But these are not showing oscillations in like single crystals.
It's not a single crystal. I shown that this is not a single crystal. It's a purely bulk material only.
Okay, thank you.
It is grown with the reflex method. With a simple, what is the mixture we added? It's a bismuth chloride liquid and tellurium powders. And we allowed it to growth to happen, that one. So that's the thing. It's not a single crystal which is expecting. Yeah.
But I think for that you need to have different kind of magnet. I mean, you have to apply the magnetic field, then only you can see that kind of oscillation.
We do not have actually because I know that that's requirement. I cannot make it out that one.
But that is really, I mean,
interesting.
That your sample can, because making this sample is really difficult. And if you have made it very single crystal, then definitely it can be used for that kind of study.
Yes,
yeah. Maybe some other question?
Someone else was asking.
Yeah.
Yeah.
No, it's on. Okay. If there is no more question, then we thank Dr. Vasundhara for nice presentation. Thank you.
Thank you, sir.
So next two presentations are online. So now we will have the presentation from Dr. Komal Kanwar. She is from Jülich, Germany. She'll be talking about the structural and magnetic properties of RCR3O complex perovskites. Dr. Komal. Dr. Komal Kanwar, can you hear us? You are muted actually.
Hello.
Yeah. So you are, okay, you have half an hour, 30 minutes. So can you start now?
Can you allow me to share my presentation?
Recording in progress.
You can share your slides.
Yeah.
So you can start.
Yeah, thank you. Good afternoon to all. My name is Komal Kanwar. I'm a Zenus postdoc at Forschungszentrum Jülich in Germany. Thank you for giving me this opportunity to present my work. The title of the presentation is the structural and magnetic characterization of rare earth orthochromite complex perovskite materials. So before going to the presentation, I will briefly talk about the purpose behind choosing this study. So if we talk about the worldwide energy uses in the overall world, we see that most of the around our world, they use the higher end of the energy, which is around 10,000 kilowatt to 100,000 kilowatt in the world. And if we see the energy consumption by the sector, we see that most of the energy consumed in the buildings, industry, and the transport. And if we see through the climate, we observe that in warm climate countries and the cold climate countries, we use energy in the water heating and the space heating as well as the space cooling applications. So this there is a every year increase in the energy usages, and we use significant amount of energy in the cooling and heating as well as. So if we see the data in the coming years, we observe that the air conditioning is increasing in the coming years, and we need such system that that create efficient amount of energy energy efficient, that should be efficient, energy efficient. And also if we see the global CO2 emission, this is also increasing with the increasing in the energy demand of air conditioning. So we need to create such a system which is energy efficient, which does not waste much energy, and as well as we need a system that minimize this CO2 emission in the worldwide. So for that reason, till now we use this vapor compression cycle, which is traditionally we used in our household. So it compress and decompress the gas to create the low temperature. But the major negative point of this vapor compression's traditional cycle is that it evaporate the hazardous gases, and also it is really harmful for the humans as well as for the global ozone layer also. So we need such system that can achieve low temperature, that can fulfill the household and as well as the global heating and cooling necessity. And so that there are different caloric effects that has been developed over the past years. One is the magnetocaloric cooling, where we apply the magnetic field, and it can change the temperature of the materials. So this can be used in the cooling systems. As well as there are other methods, such as if we change the electric field in the system, it can also change the temperature of the system by polarize the materials. Then there is another method, if we apply the pressure, so it can also change the temperature within the system. So this is called barocaloric, and if we change the elasticity in the system, then that can also be used as a cooling application, so that is elastocaloric. So the good part of these caloric effects, that these are the high energy efficient that we need in the coming years, and also these are environmental friendly, and that these create no noise, and these are safety reliability. So these are the future, we can use these in the future to overcome our problems. So if we see the publication over the past years, we observe that the magnetocaloric, in the field of magnetocaloric effect, there are huge research is going on, because these are the efficient among all of the other caloric effects. So we'll see what is the magnetocaloric effect. So if we have the system, and if we apply the magnetic field in the system, it can disturb its entropy. If we are applying the magnetic field, the magnetic moments are trying to organize in the direction of the field, so that will leads us to low magnetic entropy change. And in order to compensate the total constant entropy, the system fluctuate with the lattice fluctuation in the system will create, and that will increase the temperature of overall system. So if we remove this magnetic field from the system, then the magnetic entropy of the system will disturb again, and overall, to compensate that entropy, the temperature of the system, the lattice fluctuation will decrease drastically. So if we repeat these cycles, we can achieve really low temperature of the system, within the system, and hence we can use this cycle for the refrigerant cooling applications. So in the past years, many materials have been used for the magnetocaloric applications, such as Husserl alloys and the rare earth-based intermetallic compounds and the magnetite materials. So we chose for this particular application, we choose these rare earth orthochromites, which comes from the perovskite family, and in these compounds, the rare earth sits at the corner of this cubic structure, and the chromium sits at the center. These oxygens are surrounded by this chromium compound in the octahedra fashion. So the good part of these compounds is that these does not have the anti-ferromagnetic behavior. The spins within the systems are tilted at some angle, so this gives overall the canted anti-ferromagnetic behavior, which have the very interesting properties. Along with that, these orthochromites are not perfectly cubic in nature. There is a distortion in these compounds. So the distortion occurs due to these three main reasons. One is this CrO6 octahedra is rotated or tilted in this structure, and there's always a displacement in these cations materials from the mean position. And we also sometimes observe the octahedra distortion in terms of elongation or compression. So based on this weak ferromagnetic behavior and the distortion, these compounds have interesting properties apart from the magnetocaloric materials. One is the exchange bias. So when we have the ferromagnetic and anti-ferromagnetic layers, So if we apply the field, it creates the coupling at the surface, and due to this coupling at the surface, there's a shift in the hysteresis loop along the field axis. So this is called the exchange bias. Another property in this compound is the magnetization reversal. So when we cool down the material, it leads to the negative magnetization at low temperature. So this is the another property of these compounds. Another property is the spin reorientation. So in these compounds at low temperature, when we cool down the compounds, sometimes the spins orient in the different direction. So this is called the spin reorientation. So we choose, this is my PhD work, so we choose holmium compound for this chromite. So holmium has a large magnetic moment, and we prepare this holmium chromite using the solid state method. So the phase purity of the within the sample, we perform the XRD experiment, and we confirm that the material is single phase in nature. And with the structure in the right, we can see that the octahedra are tilted and rotated, and also there is a shift in the cations in this system. Further, we performed these magnetic measurements on these compounds, and we found out that at around 141 Kelvin, there is a ordering in the chromium magnetic moments. So it's a nil transition temperature. And further, if we see at lower temperature, the magnetization rises significantly, and there's one additional transition at 6.4 Kelvin, which is due to the ordering of the holmium magnetic moments in the system. We further fitted this magnetic measurement using the Curie-Weiss fit, and we observed the negative Weiss temperature, and also we calculated the effective magnetic moment within the system. Then we performed some hysteresis measurement on this compound, and we observed that below the above the nil transition temperature at 150, it shows the paramagnetic behavior. If we go below the nil transition temperature, it is showing the weak ferromagnetic behavior, and it is significantly increased at low temperature till 5 Kelvin. So we calculated the magnetocaloric, we did the magnetocaloric analysis on this compound, and to observe the magnetocaloric effect, there are three components. One is the change in the magnetic entropy, and one is the adiabatic temperature change. So here we did the measurement of change in magnetic entropy, and we found that in this compound, this compound shows very good magnetic entropy change at low temperature. So this compound can be useful for the low cryogenic temperature applications. If we compare the magnetic entropy change from the other chromite, it's comparable. And if we see the result from the rare earth and if we compare the data with the doped compound, which is at the rare earth side and the chromium side, there's significant increment in the magnetic entropy change. So this gives an idea that we can alter the magnetic entropy change or the magnetocaloric behavior by doping the different cations at rare earth as well as the chromium site. So for the current work, I'm working on the gadolinium chromite sample. So from the XRD, I checked the phase purity of the sample, and if we compare the lattice parameter from the literature, and the values of the lattice parameters are comparable. Further, we performed the magnetic analysis on this compound, and it shows the the fluctuation at around 169 Kelvin, where there is a bifurcation within the ZFC, FCC and FCW curve. So this shows the chromium ordering at this temperature. If we further lower the temperature, cool the system down, we see there's a negative magnetization, appearance of negative magnetization in the FCC curve. If we see further the lower temperature data, we observe that around between 2 to 3 Kelvin there's a hump in all the three ZFC, FCC and FCW curves, which is due to the gadolinium ordering. But we also see that additional peak in the ZFC curve, which is around 7 Kelvin. We further performed the Curie-wise fit in this compound, and we observed the negative West temperature and comparable magnetic moment with the theoretical value. Also from the hysteresis, we found that as we cool down below the Néel temperature, the hysteresis behavior appears strongly, which support our data from the magnetic measurements. And we further confirm these transitions using the heat capacity measurements, and we observed transition at around 167 Kelvin, which is due to the Néel transition temperature. At low temperature, we also observed a transition at around 2.3 Kelvin, which is due to the gadolinium or magnetic moment ordering. But we could not observe any transition around 6 to 7 Kelvin. So to conclude my work, in the holomium chromite, we observed the Néel transition temperature at 141 Kelvin, and there's another spin transition at 6.4 Kelvin. And we observed the magnetic entropy change at lower temperature. For the gadolinium compound, we observed the Néel transition temperature around 167 Kelvin, and this compound also shows the negative magnetization in FCC curve below 130 Kelvin. And there's also the spin transition around between 2 to 3 Kelvin. And we also observed one additional transition in ZFC curve, which is in between 6 to 8 Kelvin. So right now I'm preparing the single crystal for the gadolinium chromite, and then for the future we will see these transitions in detail using the neutron diffraction method. I would like to acknowledge the Central University of Rajasthan for my PhD work, and the Genius for the funding for my postdoc, and my colleagues from the Julius Forschung Centrum. Thank you.
Thank you, Dr. Komal. Nice presentation. Maybe we can have few questions. Yeah.
It's a very good talk. The negative magnetization, what is the origin of that negative magnetization?
In GDCRO3.
Yes. So as we lower the temperature, the gadolinium magnetic moments also align themselves, but because the external magnetic field and the chromium magnetic moments align in the same direction, but in this compound the gadolinium magnetic moments align themselves in the opposite direction of that. Because of that we get the overall negative magnetization at lower temperature.
Are you talking about the paramagnetic moment of the gadolinium? Because gadolinium ordering is very low temperature, and your negative magnetization is high temperature. So why the paramagnetic moment should align opposite to the chromium moment?
So as we lower the temperature, the gadolinium compounds start ordering. it will have the significant impact at really low temperature, but as we lower the system, as we cool down the system, it start showing the behavior. And because it's in the opposite, it's aligned in the opposite direction, it shows the negative movement. And at particular temperature around 20 Kelvin, there's a spin transition which convert the easy magnetization axis. So that's how we get the positive magnetization overall in the system.
Thank you. You were talking about transition around 20 Kelvin, but sir is asking the negative magnetization below 130. So, okay, so that may be the one possibility. Have you tried magnetization at slightly higher field? Because this measurement you have done at 100 offset. If you
yes.
At, say 500 offset, then still you can see whether this is coming negative or not. That is one exercise which you can do.
Yes, yes.
And you talked about that you plan to do neutron diffraction on GDCRO3, but for that GD is very neutron absorbing. So is it possible at your place, or you have to use the isotope of GD?
No, so I will use the hot neutrons. So I already submitted my proposal at ILL. So I will use the hot neutrons to lower down the absorption effect.
Okay, if there is no more question, then we thank Dr. Komal Kanwar. Thank you very much for nice presentation.
Thank you so much.
And the talk by or Professor Mahesh Kumar has been postponed. Actually, he is in the meeting, so maybe now we can break for the lunch. Okay. Maybe organizer can declare it.
Recording stopped.
Lunch has been served. You all are requested to kindly proceed for the lunch.
और कितनी देर बाद हम मिलेंगे इनसे?
ये जो कमेटियां बनाई थी सेशन होस्टिंग की कहाँ है?
हेलो 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 हेलो
नहीं हो सकता सही हो गया हाँ बस हिला देना नहीं और सब हाँ नहीं इतना लोड नहीं लेना
मेरे यहाँ लड़के मैंने 8 छोड़ रखे हैं नहीं खा तो मैं क्या तो कोई कर देना कमांडर सुन ले कि सर कहाँ लड़का आपका
तो ये चेंज करेगा
जो पीपीटी देगा मैम
जो पीपीटी
वो एकदम से हैंडल नहीं हो पाता ना
हेलो 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 हेलो
चलो तो
Hello.
ये वाले खत्म हो गए सभी सुमित देखो उधर रखे हुए हैं अभी अभी है 2-3 और है आईटी को तो वहाँ से मिलता है हाँ हाँ कोई इशू नहीं है
फाइल कहाँ बायोटा बायोटा तुम्हारे पास सर जो है सर वो है चेयरपर्सन ठीक है इधर बैठे हैं सब वहीं बैठे हैं माइक इधर करता हूँ सर उनका हुआ ना सर इनको देना होगा ना सैपलिंग दे देंगे ना
सर आप सैपलिंग दे देना
स्टार्ट करो थैंक यू वेरी मच वंस अगेन
हाँ जी I hope you all enjoyed your lunch today. So welcome to the second technical session of the day, and it's my pleasure to introduce our session chair, Professor Ravi Kumar. And engineering at NIT Hamirpur, where he has been serving since 2009. Prior to this, he worked as a scientist at IUAC New Delhi. Professor Kumar completed his PhD from the prestigious DIFR Mumbai in 1994. He has supervised and awarded more than 25 PhD scholars, contributing significantly to research and mentorship in the field of material science. So we are really honored to have him chair this session today. I would request Professor Sanjeev Kumar to kindly welcome Professor Ravi Kumar by presenting the sapling. Please give him a big hand. Over to you, sir.
स्पीकर बायोटा है सर प्लेट में है सर देखो माइक माइक नहीं माइक भैया माइक देना माइक
Good afternoon to everyone. Good afternoon. I think we should start now this session. In this session we have 5 invited talks. And first talk will be delivered by Professor L.P. Purohit, Head Physics Department and Director R&D at Gurukul Kangri University. Professor Purohit is around.
सर आपका लेक्चर है कोई बात नहीं सर ठीक नहीं सर पहले होता पहले आ गई
अच्छा इनसे शुरू करा दें अनुज कुमार शर्मा is also not here. Next is Dr. Anuj Kumar Sharma. Is he around? Okay. The 2 speakers are seems to be absent. And if in between they will arrive, we can start. Now let us start with the third talk by my very old friend, Professor D.T. Adroja. Professor Adroja is a at STFC, fellow at Rutherford Appleton Lab, and visiting professor at Johannesburg University, an acknowledged expert in the magnetism of D and F electron system. He has over 34 years of experience using neutron scattering and muon spin techniques. His research focused on strongly correlated electron system, quantum criticality, heavy fermion, and unconventional superconductivity. Professor Adroja has published more than 450 research papers in very high impact journal, has H-index 51, and received prestigious award like the JSPS Invitation Fellow and the Royal Society's Advanced Neutron Fellowship. I request Professor Adroja to deliver his talk.
Also, would like to thank the organizers for providing the opportunity. Good afternoon, everybody. I hope you have a nice lunch. And we'll start with the coffee anytime and quickly if you want.
Sir, वो on
Okay, can you hear me now? Okay. Yeah. So I'll talk about this magnetic ground set in the charge graph timer irradiate. And we did a lot of experiments using the various techniques. That's what I'm going to present it. This work was done by my postdoc, the Bandopadhyay. He is now back in India. So he got the faculty position, so he came back here. So X-ray and XPS work was done with this German group, Italian group, Taiwanese group. And the sample came from this Korea. And also like Dr. Chattopadhyay and Thakur were involved in some single crystal work on this same material. So a brief outline is I'll give introduction. So as I think probably you may not have heard about the ISIS facility, but you might have heard of Islamic State. But this is the different than the Islamic State. This is ISIS facility, which is this called this river in the Oxford is ISIS. Also the Egyptian god is ISIS, and that's why this is the name of the facility was given there. But nowadays, because of the Islamic State is spoiled, so we just call the Dr. Patron laboratory. Whenever we go there, we just call the Dr. Patron laboratory. So I'll talk about this facility, then introduction of the first magnetism, and then I'll put the experimental result, X-ray absorption and hard X-ray spectroscopy, photoelectron spectroscopy, bulk characterization down to millikelvin, and muon spin rotation. I'll compare with the timer-based system, and then conclusion in this one. So the ISIS facility is close to Oxford. It's just 15 miles from the Oxford, and it's just 1 hour from London. So if you're visiting London, please let me know, and we welcome you to visit our laboratory. This is a big campus, like here we have the BRC as a big campus of Indian government. This is the big campus of this UK government, Science and Innovation Campus. So we have the 2 target tests in ISIS, TS1 and TS2, and then we also have the synchrotron X-ray. So you can do all the condensed matter experiment in one campus. The TS1 was built in 1984. There we have the muon and a neutron. So this is specially for the high energy neutron. And then TS2 is built 2008, and this is the specialized for the low energy, long wavelength neutron. So if you want to diffraction, very long periodicity, then these are the instruments ideal to do those neutron diffraction there in this one. We also have the high power laser there, peak hour power. So many people do the laser spectroscopy using those peak hour power. So there are 2 target stations. If you see, this is the target here, the tungsten central of the target. So you can have any heavy metal target. You bombard with the protons, and then those produce a neutron. So this is different than what BRC. We have the reactor. You have the uranium core, which burns and gives a neutron, which is continuous source. Or this gives pulses of those, and you use those pulses to measure the time structure. So there are 28 instruments around those target station 1, and there are 13 around target station 2. Power is 150 kilowatt, and this is 48 kilowatt. So the instruments are the groups of the neutron diffraction, large scale structure like small scale scattering, reflectometer if you want to see the reflectivity of the surface, reflectometer. Then you have the molecular spectroscopy if you want to see vibration of your atom, molecular spectroscopy instrument, then you have inelastic neutron scattering spectroscopy. You can measure the phonon, magnetism, spin wave. And then we have Mu spectroscopy. These are on the target station 1. Target station 2, again we have the same, like these are reflectometer villages. So they call many reflectometer there. And this is the WIS diffractometer, which you can do long wavelength diffraction. And these are the low energy inelastic machine. And these are two under building, will come soon in operation. So this is the work basically, if you see, this is the synchrotron, is produced this proton source and high power hydrogen accelerated with the linear accelerator of 870 mega electron volt. Then you accelerate to 800 mega electron volt, which is 85% of the speed of light, and then you bombard on the target. In 4 pulses goes in target station 1, 1 goes to target station 2, and that produces a neutron, and then you collect the data and add up with the time. So we have the now next beam blast. We have the call every year to April and October. So we have next call in April 2026. Anybody can submit a proposal. This is there are different modes. Direct access means every 6 months anybody has a time. They want to write the proposal, 2-page proposal. Let's go to scientific committee. There are also the Indian members are in the scientific committee. They will review this proposal and then give you time. And then you come for the experiment and collect your data. There's a rapid, like sometimes somebody wants to publish in Nature, Science or PRL, and they don't want to wait for 6 months. They can submit the rapid proposal anytime. Within 2 weeks you'll get the result, and then you get this time, and within a couple of months you can finish the experiment and get the data. But sometimes like some PhD student wants to measure some small crystal field study which takes 5 to 6 hours for thesis, or you want to write full proposal, then you can put the rapid experiment. You don't need to write the proposal, you just put the title of your experiment. I want to measure crystal field of the holmium, and then you submit what temperature, what energy, then you send sample to us, we measure and we send you data. So these are the 3 modes worked very well in these ICs. And then we also had last 5 years, the Professor C.N.R. Rao initiated the project called this Indian Nano Mission 2017. And then 5 years we had this project funded by Department of Science and Technology. The Bangalore Institute CISC used to select the proposal from Indian user, and they used to review there, and then used to provide the result to us, and we used to provide the time to them, schedule their experiment. All this travel expense, accommodation and food, everything was provided by the ICs and CSIR. So also if you see the Dr. Jitendra Singh came there, and they visited the IC's facility. Also if you can see the Prime Minister scientific advisor was there, and they were very impressed with this Indian progress at the ICs. So after this funding, there many Indian users are coming to the ICs nowadays. And now because this funding is over, so the Professor Sundrasan has applied for another 5-year funding, and we are just waiting for the result from the DST. So this is one of the instruments. I will show few instruments, how those instruments are working. So this is the neutron diffractometer on the target station 2 is in methane moderator, so it gives huge up to 50-60 angstrom de-spacing. You can get a huge flux of those neutron. Neutron comes here. These are the positive sensitivity detector all around there. So you can do the powder as well as the single crystal. You can apply the magnetic field up to 13.5 Tesla. You can apply the pressure in same time 10 GPa. You can go down to 20 millikelvin. So all experiment you can do in one shot. So if you have any material which requires those conditions, you can do that. Also you have the uniaxial cell, and you can also apply the uniaxial pressure, and you can see the study of your material under uniaxial pressure. So as we know that everybody knows ferromagnetism, all moments are aligned parallel. If your antiferromagnetism goes up and down, then you can also have the helical structure of the magnetic moment. But if you look at this electric dipole, positive and negative charges, you can have this normally ferroelectric, or you have antiferromagnetic, plus plus or plus minus. But nobody has seen the helical alignment of this dipolar moment. And this is the Kalimani Dimitri used this instrument and showing this quadruple perovskite, the dipole moment are helically aligned. So that was the first example you obtained from that one, and that is coming from the orbital alignment of the manganese. Other instrument which I am responsible is the Merlin time of flash spectrometer. So this instrument, you have the neutron comes here, and there are the choppers, various choppers which chop the beam, select the energies, and then this is your sample, hit the sample, and it diffracts, neutron scatters it. And these are the detector, 3.5 meter long detector, positive sensitivity 180 degrees. At 2.5 millimeter where neutron is hitting, you can find out it. So that means you can measure the 4-dimensional Qx, Qy, Qz energy, and then you can get all the sort of measurement in one go. And because of this time structure, you can use one energy, but you can get free extra 3-4 energy. So you don't have to measure the all different energy. You can get from 7 MeV to the 200 MeV or up to 2000 MeV in one go. And you can see these are the one of this compound which has a chromium dimer, and Bela Leck from the Germany did this experiment, and you can see the dimerized structures in this material. So this is basically, if you look at the BRC triple axis, you go point by point. Then you miss what is around this one. While this one you collect the data, then after a month you want to see what's happening in this area of this reciprocal space. You can look at the data, you have all the data in one go. This is the other instrument called LET, which is in targetation 2, and this is the low energy spectrometer, same as Merlin, but this is the detectors are 4 meter long detectors, and again you have huge amount of the SQ omega space, and then this allows you to go to the micro electron resolution, so you can go to 10 microelectron resolution, so you can come with instant energy 0.5 MeV up to 30 MeV, and you can collect many energy together. And this is one of the compound studied by this Michael Schmidtman from this China. So this is cerium antimony 2. If you apply the pressure, it becomes superconductor. So it's heavy fermion superconductor. And Michael did the experiment from this excitation. He can fit all these exchange as a J as a ferromagnetic and the weak coupling between these two. So it's a quasi one-dimensional ferromagnetic interaction. And if you have ferromagnetism, you can get the spin triplet superconductivity. Normal BCS coupling, you have the antiferromagnetic coupling. Spin are singlet, but this is the possible spin triplet superconductors. And then now let me go to the frustrated magnetism. So as we know, in frustrated magnetism, dimensionality is very important. So if you have the 3-dimensional structure, which is pyrocle lattice, then you have tetrahedral connected with this corner. And now if you try to put the spin on those one, then you cannot satisfy all spin antiferromagnetically. Those spin are frustrated, and those frustration gives you the huge amount of novel physics. And this is one of the things is spin ice, they call it. They call this magnetic monopole, because if you have the magnet, you cut in the 2 parts, you get north-south, north-south. You cut another 2 parts, you get north-south, north-south. You never get the south or north. But you can study the south pole or north pole physics by using this pyrocle lattice. And that's the monopole physics in that one. In 1972, the Anderson proposed the lattice called the triangular lattice spin liquid. So and based of that, he used the RBB valence bond resonance theory, which is the origin of superconductivity. And here again, if you icing spin on this one, if you put one spin up, other spin down, this spin doesn't know where to go there. If you put down, then this is ferromagnetic, which is high energy. If you put up, then this is ferromagnetic, high energy. So that means this spin is frustrated, and you get this quantum spin liquid. That means you have long-range entanglement, but it doesn't order magnetically, and this is quantum spin liquid behavior, which has application in quantum computing. Then if you connect those triangles by this corner, you form the Kagame lattice. So this is the Japanese basket of the Kagame, and this lattice is again this frustrated lattice. And this lattice is very important for the charge density of superconductor. Recently people have observed it. And then you can get the current, chiral current. Current loops goes in this chirality, change the left and right chirality. And this is very important, also topological flat band in the Dirac mode. The Kitave theoretically produced that if you have the honeycomb lattice, if you put the spin up on that one, you can produce the ground set is non-magnetic entangled ground set, and that's called the Kitave spin liquid. And this ruthenium chloride was also discovered by using one of these instrument ICs, and that has again there's 2 types of things, Majorana fermion, which is its own antiparticle. You can determine the Majorana fermion in this one of these lattice, and again you can have the gauge flux. So you have the 2 different kind of particle you can determine by using those lattice. Now if you reduce the dimensionality one-dimensional, so if you isotropic one-dimensional lattice, which doesn't order magnetically, and you have gapless excitation. But as soon as you have nearest neighbor and next nearest interaction start competing each other, then again you get novel physics of like Tominaga-Luttiger liquid, dimerization, and if you put spin 1 on the one dimensional, you get the Helden gap. So these are the dimensionality is very important in this one. So now if you look at the transition metal, why transition metal are very important? Because a lot of new property has been observed in transition metal. One of these is quantum spin liquid behavior. And now if you look at this transition matrix, you pull the D band, you have this band here, there's no Coulomb interaction, no exchange, no spin orbital coupling. Now if you put the spin orbital coupling, this split up and down Hubble band, and this is basically mode insulator which has the electron volt gap. And from mode insulator you get the superconductivity, high temperature superconductivity. But now if you put the spin orbital coupling, then again you get J effective band, because if actually J state split up and down S minus L, so you get this J effective band. But now if you combine these two, then this band splits in upper and lower, and then this is called the J effective spin half. And because the J effective quantum number is small, you have quantum fluctuation, and again you get the spin liquid behavior in this one. And these are one of the example of the iridium 4 plus has a 5 electron, and you can see the physics in this one. There is a 5 electron there. Crystal field will split those electrons, and then spin orbital coupling will split and give the J effective state here. If you have just spin orbital coupling, you get this upper and lower band here. And these are the different structures when people have observed it. But in this, if you go 3D to 4D to 5D, you have the change in the bandwidth is very big in 5D. If you go from 5D to 3D, you have the U and the J's are increasing, while here the spin orbital coupling and crystal field is decreasing. So there's a competition between these two parameters, and you can produce a lot of new physics by using those combination of those two parameters. Here you can see if you have the Hon'ble coupling is bigger than the crystal field, you get a bigger spin. Or if it's small, if it's smaller here, you get spin 1, and the other thing you get the J0 state. And these are the phase diagram where the iridium are sitting there. So iridium, because you have the orbitals, and orbitals has the interaction with this oxygen, so you have Coulomb interaction, and because of those it splits in the 2G, so those are the same energy and Eg. So in the octahedral crystal field you can get the splitting of the two. But now you can stretch the octahedra, and then you can get the splitting of those band, this band. If you compress the octahedra, tetragon distortion, you can get the singlet ground state or doublet ground state. Same thing you can do this trigonal distortion, compress or this one, you get similar physics there. So this is the paper which I am going to talk to today. This is the paper which published in the Physical Review Material. And so the structure of this compound is very long C-axis. Now if you can see here, this is the interesting unit. There are 3 iridium atoms sitting in this one. So that's called the iridium 3 oxygen 12 trimerization. First central one has a different nature than these two. So these two are same, so then you have this similarity here, and this is different. And if you look at the iridium distance is very small, it's a 2.53 angstrom here. And also this inversion center is there, so this one has inversion center there. There are 2 types of oxygen there. So if you look at this one of the unit here, around the iridium 1, which is isotropic, the bond length is 1.94. If you look at this unit, you have this oxygen 1 and oxygen 2, and there are a little bit different distortion in this one. If you look at the AB plane of this one, then in this one you can see triangular, so which are giving the source of the frustration, and the system doesn't order magnetically because of the frustration. If you look at again the iridium to this position, again you can see the triangular, and along the C-axis they are coupled in the ABC axis in that one. So we did the X-ray diffraction of this one, and X-ray disorder the sample is single phase. But if you look at the site ordering, there's a 10% disorder. The iridium goes, 10% iridium goes on the niobium site. On the vice versa, there's iridium 1, iridium 2 side, the niobium, same amount of niobium goes on the iridium side. So there's 10% disorder in this material. And which will also use the X-ray, if you do the L3 absorption, near and extended edge, you can find out from this your interference pattern, because if outgoing, incoming photons have different interference, and those interference will give you the number of the cell around this your probe atom. The probe atom is iridium, so you can find out how many cells are iridium, neodymium, niobium, and all that one. And that again gives you require 10% disorder to fit those data. So that means there's 10% disorder in this material. So then to like Ravi Kumar showed you about the X-ray absorption. So if you do the X-ray absorption, you can probe the excitation from core level 2p to 5d, and that gives you valence state of this your probing atom. So here we probe this iridium atom, iridium L3H, and then you can see these are the 2 iridium, or 2 has iridium 4 plus. This one has iridium 3 plus, and this is our sample. So it's not 3 plus, it's not plus, in between. And that is what, if you calculate the charge neutrality from the chemical formula, its valence is like 3.67 in that one. And also we didn't see any evidence of the 5 plus here, because if you have this neodymium, if iridium goes there, if it changes the valence, then you should get another signal of 5 plus, but it's no 5 plus. That means wherever iridium goes to niobium side, it keeps same valence, and when niobium goes to iridium side, it keeps same 5 plus valence. This is the niobium L3H, and which again the niobium is 5 plus, and this doublet is coming with the crystal field effect in this one. But the valence state of this both one are known now, 3.67 in iridium and 5 plus in niobium. So then, like, we can do the X-ray photonic spectroscopy. If you lab-based photonic spectroscopy, you see the surface effect. But if you go to synchrotron, if you do the hard X-ray photonic spectroscopy, you can see the bulk one. And what we can see here, that these two peaks, which can be spin orbital coupling, splitting of this F band and also this deep iridium D band, and you can see those you can fit with the iridium 4 plus and 3 plus. The average valence comes like 3.61. There is no evidence of iridium 5 plus in this one. Here this niobium again is spin orbital coupling 3 MeV, and then you can fit by theoretically the niobium 5 plus. This is the valence state there. Oxygen is 2 minus, but then there is the iridium niobium disorder, gives you 10%, which is the signal coming from here, which is the disorder state, which it tells you because of disorder you get just a solder in this one. So then this XPS we did it, so you can calculate the XPS by using the DFT calculation, and these are the data. First thing you can see near the Fermi energy, this is the gold one, has a lot of gold is metallic, so you get a lot of electron near the Fermi energy. But in our sample there is no much signal near the Fermi energy, which is telling this sample are insulator or semiconductor. And this is the confirmed from DFT. If you look at the DFT calculation, here there is a gap in the DFT calculation. And what DFT is telling, that a lot of oxygen bands are there, a lot of iridium bands. Iridium bands are dominated by this around 1 MeV and 8 MeV. So these are the bonding, anti-bonding orbital of the iridium. And they are also telling the hybridization between the iridium and oxygen band. Iridium mostly 5D jet square bands are dominated in the iridium case. These are this one. And once you have this density of state, you multiply the cross section, and you can get the same simulated spectra, and you compare with the theory. So which is the good agreement between these two. And then you measure the resistivity to check with this insulator, and again the resistivity goes up and it's insulating behavior. And from this activation you can find out the gap of this 0.25 MeV. So now then we want to see the spin orbital coupling. As I mentioned, the spin orbital coupling is very strong. You get a J effective half state. If spin orbital coupling is small, if hopping is bigger, then you get the molecular orbital formation, because then this hole will move one iridium to second iridium, third iridium. The whole 3 iridium becomes molecular orbit. And in our case, we wanted to calculate what is the strength of spin orbital coupling. And so you have this iridium L3 and L2 ages data. So if we use this ratio, they call it branching ratio, and from this one, under this of this area, you can find out what is the ratio. Ratio is coming 3.1. And this is basically your expectation value of the spin orbital coupling parameter. And now if you look at this compound, which are the strontium to iridium 4, which is J effective state with strong spin orbital coupling, 5.1. So what is telling in our case, spin orbital coupling is moderate. That means J effective bands are not separated, 3.5, they are mixed band, which again agree with our band structure calculation. And then you can compare this data with this whole range of this strong spin orbital coupling, where all this branching ratio comes, the ratio of the intensity of the L3 and L2 is coming 5, but in our case it's somewhere like 3 plus 1 here. And this is same you can see in the double perovskite, where you have this weak spin orbital coupling, is same agreement with our case, that spin orbital coupling is very weak. So then we did the resistivity and magnetization measurement and acid susceptibility measurement down to millikelvin. We have the laboratory where you can use this PPMS, MPMS up to the 50 millikelvin. And many users from India are also using our facility. They send sample and we do measurement for them. So you can see the acid susceptibility at various frequency doesn't show any peak. If you have spin glass, you see the maxima, and peak will increase with the frequency, but there's no change in the frequency here. and no peak. That means there is a paramagnetic or quantum entangled ground state. If you look at the susceptibility, there's small glitch here, but that could be tiny ferromagnetic impurity which people see in iridium-1, most of iridium compound. But if you look at the effective moment, it's 0.3, which is much smaller than the J effective moment, or even like a iridium spin half is smaller than that one. Theta P is minus 17 degrees, that means sizable anti-ferromagnetic interaction. It should order magnetically, but it doesn't. If you look at the low temperature susceptibility versus temperature, it shows the power law behavior. And this power 0.45, which is the people have seen in quantum semi-liquid material, and there are a lot of low energy excitation, which gives the power law behavior here. So same thing with magnetization, if you use it, you can fit the Brillouin function. Brillouin function doesn't fit very well, and this power law fits very nicely. And now if you look at this power law, this beta is 1 minus alpha, which is observed in quantum semi-liquid material. And then magnetization, basically, if you increase this temperature, magnetization comes down. So I'll use those data to the scaling, and also I'll measure the susceptibility at different applied field, and then you can do the thermodynamic scaling of this one. These are the single crystal data of this Chattopadhyay. They have made the disorder in this material, and they call the disorder dominated power law behavior, but they don't call this quantum spin liquid, but they say disorder is changing all this behavior in this material. So then we measure heat capacity down to the 50 millikelvin, no ordering there. You can use the calculation of the phonon Einstein mode, Debye Einstein model, and then you can separate the phonon, and you can see some phase transition, which is mostly people see once you go from paramagnetic, the quantum entangled state, you get some transition in the heat capacity there. But the entropy is only 10%, so that means still a lot of disorder in this material, spin disorder in this material. If you look at this low temperature, the C by T goes up in zero field, and you apply the field, you get the peak, which is coming Schottky type anomaly. And by fitting those things, you can get this splitting versus field, which is linear, and that gives you the G effective J value. And J is roughly close to 2, which is the free electron in that one. So this is the basically we see there are some free spin, which gives you those behavior here. And the gamma value, and this is the T square component, which you expect if you have the spin-on excitation, Dirac type physics, you can expect the T square component, and that this value of this coefficient of function of field, so weak dependent, while electron coefficient gamma goes a little bit down here. So again, this heat capacity telling there is a no long range order, some Dirac type physics in this material. And then using the various susceptibility, you measure the susceptibility various temperature. You can do this T by H, all different field, and you get H by power alpha and susceptibility. You can scale all data in one universal curve. And this is called the thermodynamic scaling. You can do same thing if you measure magnetization, as I showed you previously, one various temperature. Again, you can do the scaling, and these two experiments are related in quantum spin liquid behavior. But people have shown some scaling in heat capacity where you have the random singlet. It's not uniform lattice, but you have random singlet here and there. And then they see the scaling in the heat capacity, but we don't see scaling here. So what we see, the quantum spin liquid behavior comes from homogeneous lattice with 10% disorder is not playing much role in this low energy excitation. And then muon spin rotation. So the muon is very nice probe. And if you have tiny particle, if you have very weak field, muon will see those fields. Neutron diffraction fails to see small moment, but muon will see the big moment. And that's why muon relaxation is very important. It's also for superconductor, if you measure the penetration depth, and you can find out your triplet pairing or singlet pairing by using the muon spin rotation. So the muon, we have this various instrument there. This is the, before this proton beam hits to the neutron target, there's a graphite. So you have carbon graphite. Once muon hits this 2% of the beam to this graphite, it gives the pion. Pion decays in the muon and a neutrino. And you collect this muon, and thus muon comes and implant on your sample, and muon will, if there is internal field, it will precess it. So we have the three instruments which was the European built by there, and this was built by Japanese, but now Japanese has left and they have given all instruments to ICs now. So all facilities now, the muon, there are 6 instruments are belong to the ICs facility now. So these are the typical spectrometer. These are all detectors. The muon beam comes from here, and the central sample is sitting there. The muon precesses, because depending upon which direction is within the 2.5 microsecond, muon will decay in positron, and it will emit the positron. You detect the positron in the count in this one, and from positron count you can find out what muons are doing in the material. I see like this is the precession frequency of the muon. And precession frequency directly depends upon your local field. So you can find out local field, but if you're ferromagnet, you get bigger field, anti-ferromagnet, smaller field because of cancellation. And this is, it doesn't depend upon the angle. It's just basically position of the muon at particular position in your sample determine the frequency. So this is the typical example. This is the muon is coming there. This is your sample. So muon see the internal field is precessive. And then if you use ferromagnetic compound like Professor Ravi Kumar one, it will show this frequency. But now suppose I have in this sample the different field is not all the homogeneous field. I have inhomogeneous field. The muon will start decaying it. So if you see here, the muon now start decaying it. So I can see that I have the field in my sample is magnetic order, but the fields are not homogeneous. So there is some random. Suppose you have this one rare earth, this is moment 2, other has 6, third one has 8. Then you get random field distribution, and that shows the decays. But if you don't have any ordering, then you just decays. Then nothing is happening in the material. It's just quantum or parametric fluctuation, which you measure the spin lattice relaxation in the NMR. Same thing you can do here. So this is the basically sample which we measure it. You can see the muon. You put this silver plate, put this sample on that one. Muon comes here, and you detect this positron forward and backward. And this is the positron asymmetry. You measure it. You can see up to millikelvin, the signal is, there's no loss of the signal. First thing, there's no oscillation. If you have oscillation, then you have magnetic order. There's no oscillation. If you have very high moment, the muon doesn't see oscillation, it just loses 1/2 of the signal will lose and then remain constant. So there's no loss of the asymmetry, there's no sign of the oscillation, which clearly tells you that this system is the paramagnetic system down to the like 100 millikelvin. If you increase the temperature, so this relaxation is decreasing, and that tells you how your spin fluctuation are changing in your system. So you can fit those using these two components. So you have this stretch exponent power here, and then exponential behavior. So you have the two sides of this muon. So we tell this side is coming from the disorder side, this side is homogeneous side, and which agrees, because this is the telling volume fraction A1 and A2, which agrees with 10% volume fraction in our material, which is disorder side. What we see is the relaxation of this order homogeneous side is increasing, then suddenly it goes up and flattens it here. And this is the typical, once you have the quantum spin liquid, you have a lot of low dimensional, low energy fluctuation, and you can see this type of typical behavior coming from quantum spin liquid. And this side disappears up to 6 Kelvin, only shows this something in the 6 Kelvin. So this behavior clearly tells that this material is a quantum spin liquid, the iridium are entangled state in these materials. And then you can see whether those are dynamic or is coming from the nuclear moment. Sometimes you have nuclear moment, and then muon will see the nuclear moment. So because nuclear fields are very small. So if you put the field of something like 15 Gauss, this line should become straight. But here with 15 Gauss, it goes there, and then again continues up to 3000 Gauss, which tells you these are the electronic fluctuation coming from iridium moment. And then again you can fit this lambda as a function of the field, which gives you this basically fluctuating field, which is 4.8 Oster, and then this gives you the basically fluctuation rate in megahertz, which are again you observe many quantum spin liquid system this time. Second component still behave little bit unexpected. It should have gone like this, but still there's something is happening in the second component, which need to initiate more in this one. But basically it's telling me also the quantum fluctuation, dynamic fluctuation in this material, and again support the quantum spin liquid ground state in this material. So if I measure the other two compounds, this is ruthenium, again here ruthenium timer there, which is more magnetic, and the rhodium, again here rhodium timers. These two rhodium 1 and rhodium 2 sides are completely distorted. They are two different octahedral environment. So here we tell the lambda 1 and lambda 2 is coming from the two rhodium side. There is no disorder in this material. So these are both materials are the isotropic, and then again is relaxation rate behavior completely telling there is no ordering down to this like 300 millikelvin, and here is something like 250 millikelvin. So these two again support this is dynamic quantum spin fluctuation behavior in this material, and this one is under preparation while this is published there. So here basically I'll put my conclusion. So we investigate this irradiate by using the multiple technique and DFT calculation. The XRD and L3H exam show there is 10% side disorder between iridium and niobium. Iridium L3X measurement show this and a core level XPS confirm the iridium valence is something fraction valence. It's not 4 plus, it's not 3 plus. So what's happened if your hole is hopping between the 3 iridium sites, you form the molecular orbit. And this is what picture is coming, molecular orbital formation, and which is supported by the band sector calculation. Also the RIX, people did the RIX from this, the German group did the RIX measurement at ESRF, and that also support the quasi-molecular formation in this material. Branches ratio study show this spin-over coupling is not strong, so it's weak one, and that again support this behavior here. Band sector calculation show the possible molecular orbital formation. The XPS and registry show the energy gap at fermium energy, which is supported by DFT. The CISC, DC and heat capacity come from the absence of the long range magnetic loading down to 50 millikelvin. Heat capacity supports the Dirac type physics, spin-on excitation at low energy. The MEOSA provide the dynamic and quantum fluctuating ground state, which is the entangled ground state, which is quantum spin liquid behavior. So I would like to thank you very much for your attention, and also Professor Neeraj Panwarwar and Professor Malik, and also the thanks to the funding agency from Royal Society and PPSSC UK. Thank you very much.
Any question? It's an interesting talk, which include a lot of physics part and really seeing various kind of phenomena using neutron and muon and including the photons also. So he has coupled all the things together. As I was talking about photons only, he has talked the neutron and muon, looking at the structure, and along with the bulk technique like specific heat, magnetization, resistivity, and the local probes like neutron and muon and photons. So, any question?
Yeah, if you have question on the facility access, I'll be happy to answer the available instrument and facility.
So if there is no question, let's thank.
Thank you very much. Thank you. Thank you very much. Thank you. Thank you very much. Thank you.
Nice talk.
Yeah, thank you
And
for
I
the
have learned a lot.
Thanks. Yeah.
And next speaker is Dr. S.D. Kaushik. He is scientist G at UGC DSIR Mumbai Center. Major research interest include establishing correlation between crystal, magnetic structure, and physical properties of strongly correlated electronic system, primarily based on transition metal oxides, the variation in crystal and magnetic structure driven by doping, substitution, temperature, etc. are characterized through neutron diffraction as well as another physical characterization. This talk is again on a neutron diffraction based techniques. He is involved in studying magnetic material, exhibiting multifunctionality and quantum nature. He is also working on intermetallic and Husserl compounds. And I request Dr. Kaushik.
Thank you, sir. It's a pleasure to be here, and it is my first time that I am visiting the Meerut, this CCS University. I would like to thank the organizer for inviting me, and it is a pleasure that Professor Ravi Kumar is my chairman of the talk, and Professor Adroja has given the talk before me. So both of speakers and chairman I know very well, and during my PhD I had worked with Professor Ravi Kumar, so it's a nice background for me. And I would like to have more interactive kind of talk, because you people, I think most of you are in MSc or early stage of PhD. So it'll be basically, though the talk looks a bit complex, but I will try to start with the facility which we have from where we are. So basically, I belong to the UGC DAE CSR Mumbai Center. So basically, this the organization UGC DAE Consortium for Scientific Research. This is a basically inter-university consortium which was established in collaboration with Department of Atomic Energy. It was established in 1989. So basically, Department of Atomic Energy, BARC, and RRCAT and all. So these are many Department of Atomic Energy facilities, and not very easily accessible to the university users. So to make them available, make these facilities available, because these facilities are large scale facility, cannot be replicated in any university just like that, because it requires lots of fund and all. So because of that, we are here to facilitate these facilities, and we mandated to promote and coordinate and encourage university users to use these facilities at no cost to the user. So these facilities you can use without any cost. We don't charge any funding from you. In fact, we provide the funding in terms of, if you are coming to use our facility, then we provide TA and DA. And then it was initially named as IUC DAEF. It was renamed to UGC DAE Consortium for Scientific Research in 2003. So presently we have 4 centers. Mumbai Center takes care of the neutron-based facilities. Indore Center looks into synchrotron-based facilities. Kolkata Center is looking into the cyclotron-based facility. And Kalpakkam is more involved in multidisciplinary facilities. And then we have another node which has come up in IOP Bhubaneswar, that is also in just now started. So soon it will be open to all the university users. So if I talk about how many users are coming, or so, I can say that in last, if you see this is up to 23. Last 2 3 it has not been added. So typical number of university universities involved. So roughly around 200 universities are being catered by the Indore Center, and then Mumbai Center and Kolkata Center and Kalpakkam are a bit smaller. So the total number, you can say more than 300 to 350 universities are using our facilities. And if I talk about the number of the users, so number of the users is almost 1500 per year. So 1500 per year we are trying to cater, but still we would like that you are most welcome to visit these facilities. And because I'm also here to ask you, because we have less number of users from this area, but if you look into the users from all across India, we are trying to cater as many as users as possible. And coming back to our Mumbai Center, so Mumbai Center basically looks into the neutron facility, which comes under National Facility for Neutron Beam Research, and we coordinate neutron facility at our center. And in addition to that, we also have our in-house facility which can be complementary to neutron facility. And the way, how you can use these facility, as Dr. Adroja has also mentioned, that there are 3 ways in to access the facility at UK. We have 2 ways. One is one-time proposal. If you have, say, any experiment which you want to do only on 1 or 2 sample, you can write to us for just for that you want to have these kind of facilities. So one-time proposal. And another option is 3 years proposal. So once you submit the proposal, and if it is accepted, then you can have committed user facility, access to that user facility for 3 years.
So right now the proposal round is on. So this is, the last date is tomorrow, but it is likely to extend maybe by a week or so. And so far at our Mumbai center, more than 300 long-term CRS proposal have been completed. So this is one proposal is 3 years, so we can say we have catered more than 300 long-term CRS proposal. And then if I talk about neutron scattering facility, so neutron scattering facility are now limited to this Dhruva reactor. The ISIS facility is based on this spallation source, in which you have to use a high energy electron to generate the neutron in the form of pulses. But here the neutrons are generated from Dhruva. This is reactor based source, in which there is a controlled chain reaction taking place. Through controlled chain reaction we can have continuous flow of neutron, and then these neutrons are being used for the neutron related facility. So using neutron, there are many facilities are possible. So this is one facility which I will be talking about. But other than that, when we talk about neutron, so neutron is a chargeless particle, and it is a spin half particle also. So due to chargeless particle, it can go very deep into the sample. It can penetrate very deep into the sample. So that is benefit over X-ray, because we can study neutron diffraction, which will tell you the crystal structure. But you may say that we can study the crystal structure using X-ray also. So what is the benefit of neutron having over X-ray? So that I will talk about in next few slides. And then neutron, it's a spin half particle. So because of spin half, we can use them as a tiny magnet. So because of this tiny magnet, they can interact the magnetism present in your sample, and then it can give magnetic information also. And moreover, these are thermal neutrons. Thermal neutrons, so they have typical energy range, typically around 100 up to 100 millielectron volts. So these thermal neutrons can also be used to study the lattice dynamics present in your sample. So neutron scattering, or it will give you the study of dynamics present in your sample. So that is the way neutron can be used in this different techniques. So collectively we call neutron scattering. But when we are looking into the elastic scattering, so it is giving you the neutron diffraction. So neutron diffraction, so depending upon uses, you have different kinds of instrument, and different kinds of instrument have their own design and limitation and facilities. So coming back to other facility, we have other facilities apart from neutron diffraction. We have synthesis facility, in which you can synthesize sample by different methods. So this is typical solid state reaction method, in which you you take the amount in the stoichiometric ratio, and then use solid state reaction method using furnaces and all. And then one option is this is called ball mill, and this can be used to have a top to bottom approach, and it means you can prepare the nanoparticle just by grinding them very finely. So this is ball mill you can use. And then this is arc melting system. In arc melting, you can make metallic sample or intermetallic sample, because for arc melting sample, when you have a metallic kind of sample, so this cannot be made by solid state reaction method. So you need to have very high temperature. So very high temperature can be possible by using kind of arc, by producing arc for a fraction of time, and then you can have a new phase of sample. And this is new technique. I would say this is spark plasma sintering. In spark plasma sintering, we can have simultaneously high temperature and high pressure. So we can have 2000 to 200 degrees centigrade temperature, and we can go pressure up to 50 kilonewton. So 50 kilonewton means in terms of GPa, we can reach up to 100 GPa, 100 megapascal. So this is very useful if you have if you want to control the grain growth. In process of grain growth, you can bring the grains together and decrease the grain boundaries. So in this way, if you are using multiferroic kind of sample, in which grain and grain boundary conditions are giving rise to limitation of the magnetoelectric coupling, and also these things can be studied, or can be improved by using spark plasma sintering. So for apart from synthesis, for characterization, we have X-ray diffractometer. This is a tabletop X-ray diffractometer, very useful to identify the phase formation and all. And then we have 9 Tesla and 14 Tesla physical property measurement system. So these systems can be used to characterize DC and AC susceptibility, and then heat capacity and electric and thermal transport. And now recently we have got this cryo-FMR also. So cryo-FMR is also useful to study this small amount of magnetism. And then we have this broadband dielectric spectroscopy, which has a frequency range from 3 microhertz to 3 megahertz, which can go up to gigahertz. So this is broadband dielectric spectroscopy. Then we have a PE loop tracer, which is having 10 kilovolt power supply. So means polycrystalline sample can also be used for PE loop study. And then dynamic light scattering. So these facilities are available to free of cost. If you want to use these, you can use, and you can write to us, and then these can be used. So now coming to outline of the presentation, actual presentation. So basically, as the topic suggests, this is double perovskite kind of compound, and I'll be talking about what is double perovskite, and then why we wanted to use or we wanted to study that kind of compound, and then some structural characterization and physical properties, and some small amount, neutron diffraction I'll be talking about, and then conclusion. So if we look into it, in the morning also there was a discussion that if we can have different kinds of perovskite compound, they can be very useful for defense application and all. So perovskite compounds are basically ABO3 kind of compound, in which you can have A site and is occupied by lanthanides or alkaline element, and B site can have the transition metal element. So this is general formula of ABO3. If we replicate it 2 times, then it becomes double perovskites. So double perovskite means basically you will be having different different transition element at B site. So basically it is divided by, or maybe we can say B dash type. So it will be A2 B dash O6, this kind of perovskites. So these double perovskites are very useful in terms of by using A, different elements are possible, and B dash, there are different elements are possible. So basically it gives large applicability, you have large option of replacing A site and B site, and then it can be large electropositive cation or small transition metal ions. So this will give you a possibility of exploring many things, and once you prepare the compound, you can characterize those compounds for different applications also. So in this particular study, we have focused on 2 kinds of compound. One is TB2-CEO-MnO6, another is TB2-NI-MnO6. So basically the idea is that when we study the TB2-CO-MnO6 and TB2-NI-MnO6, why we wanted to study? So the reason is that when we looked into this literature, we could figure out that in case of TB2-NI-MnO6, there is a possibility of impurity phase, which is typically 4 to 5%. So this impurity phase could be because of synthesis process, or synthesis process has not been very sorted out. So the impurity phase in terms of CO3O4 was there, or sometimes TB2O3 was also there. And because of impurity phase, there is a different kinds of effect is coming in terms of magnetism, because CO3O4 and TB2O3 are magnetic in nature. So the real magnetism will not emerge from this kind of compound, which is having some impurity. And if we look into some other rare earth based compounds, so we could see that in case of HOMNO3 also there were huge amount of impurity of HO2O3 in case of HO2-NiMnO6, and in case of HO2-COMnO6 there is another huge impurity. So literature, there is no consensus as what is the actual magnetism for this kind of compound, because of impurity phase there can be effect of impurity. And then we also wanted to study that if we change the one element at B dash site or B site, if we change from CO to Ni, how the magnetic properties or physical properties are changing for this kind of compound. So that was our goal, or motivation we can say. So in this process we have synthesized this compound by modifying or by looking into, we have prepared this compound by using solid-state reaction method only, but we have spent a lot of time in identify the actual synthesis condition so that we get the single phase compound. So we have tried many options of heat treating at different temperature, and characterize this sample with using X-ray, and we could finally make this compound single phase. In fact, both the compounds single phase. So in this synthesis, once synthesis was completed, so then we have studied the structural properties and physical properties. So for structural properties, we have used X-ray diffraction and neutron diffraction, and then surface morphology. And in case of magnetism, we have done DC magnetization, temperature dependent isothermal magnetization, and temperature dependent neutron diffraction. So temperature dependent neutron diffraction, why I am talking about in physical property, I'll come to this point in next slide. So as I mentioned, when we do the X-ray of any sample, so if we are using X-ray, so using X-ray we see element like this. So because the reason is that intensity of the X-ray is follow the law which is having Z in that formula. So because of this Z, so we see the element like this. But in case of neutron, if we are using neutron for looking into the diffraction, so the intensity depends upon the scattering length. So scattering length is not following any formula. Scattering length is an inherent property of the element, so which is going like this. So because of this property, we see the element like this. So the benefit of seeing element through neutron and X-ray, you can immensely identify that if there is a possibility of having two elements which are nearby, it is not possible to identify using X-ray, but it is possible to identify using neutron. So suppose Fe and Mn are there, so there is a difference between the scattering length. So you will see these elements differently. So using these two elements differently, you can identify which element is coming properly. Another benefit of neutron is that in case of atomic form, in case of X-ray, there is a form factor dependence. So the effect of form factor dependence is that if you go to the higher 2 theta value, so because of higher 2 theta value, you will see the intensity are falling very rapidly. But in case of neutron, it is not having any form factor dependence in case of structure part. So benefit of having no form factor dependence on neutron, you will identify when you analyze this data. While analyzing this data, you need to fit, you need to give some model, and you need to give, once you give some model, then once you get the data, this is data which we have collected on our instrument. So this is X-ray, you can see at 1.5406 angstrom X-ray wavelength. So the peaks are rapidly decreasing, and even at 75 degree or so, 2 theta value. But if you do the neutron at closely 1.48 angstrom, so the neutron peaks are very, it's not decreasing very rapidly as compared to X-ray. So this is the benefit of using neutron. And then once you analyze this data, in analysis what we do, basically we give some model in which your space group and atomic positions are given, and based on that you can try to calculate the similar kind of observed pattern. And once you get the observed pattern, you can see what is the difference between an observed pattern and calculated pattern. So if this difference is as flat as possible, it means your model is correct. So once your model is correct, then you can identify that your model is very close to reality if these peaks are quite high intensity as compared to this. Because if you are fitting this kind of data, fitting these peaks will be very easy. But if you may have misleading model, but if you are fitting these kinds of peak, the chances of getting error will be less. So that is the benefit of using X-ray. And moreover, as I talked about that neutrons are chargeless, neutrons are spin half particle. So you can get idea about the magnetic ordering. If it is ferromagnetic ordering, so ferromagnetic ordering means you have spin which are in one direction. So the reference of this will be seen in the enhancement in the pre-existing peak. In case of you have antiferromagnetic ordering, you will see that your crystal cell is basically half of the magnetic cell, because in magnetic cell you have a similar kind of magnetic ordering at the second interval. So basically crystal cell is this, so you have magnetic cell is like this. So because of this doubling of the crystal cell in terms of magnetic cell, you will see the new magnetic peak. So just by looking into the neutron data, you can have idea that whether this your sample is ferromagnetic or anti-ferromagnetic in nature. So that is another benefit of neutron. So I can say if you look into the any characterization using X-ray, so we can just have idea that these are the trunk, how the atomic atoms are placed in this. But using neutron, you can have idea that how the magnetic spins are oriented over there, and then it will give idea that how the leaves are there. So this is our neutron facility. You can definitely go to ISIS for neutron diffraction experiment and neutron scattering experiment, but you can come to us also. And we don't take much time. You can write to us anytime, and then we can tell you either you can come or send your sample, so we can quickly do the experiment. At least it will be helpful once you have the neutron data. So it will be helpful to write a proposal to ISIS, and then chances of your proposal getting accepted increases if you have some primary data. So basically, this is our neutron diffraction facility, which we have our colleagues at our Mumbai center have installed this. So this is basically neutron beam getting monochromatized and using this silicon doubly focusing monochromator single crystal, and then it is falling on the sample. So we are not having very hi-fi detectors. We are only having this linear detector, 1D detectors. So neutron diffraction, diffracted neutrons are collected by these detectors, and then we get this kind of pattern. Once we get this kind of pattern, so then we can fit the data and do the analysis. So we have the option of having room temperature in air, and then we can go down to 2.7 Kelvin and from room temperature, and we can apply the magnetic field also up to 7 Tesla. And this is actual neutron beam which is coming out of this neutron after monochromatizing. So this monochromatizing means it is having constant wavelength, so it means having constant energy. In this process, basically we are following the Bragg's law, and then using Bragg's law we can have constant wavelength neutron. So since the time is limited, so you can look into this all the facilities available at the BRC. So this NFN, if you type NFNBR neutron scattering neutron instrument booklet, you can find this booklet in which all the informations are given. So coming back to our work, so we have characterized, we have synthesized the compound by X-ray diffraction. We have synthesized compound by optimizing the synthesis condition, and then we analyze this data on TB2CMNO6 by X-ray and neutron. So you can see the fitting is good. So this shows that there is no signature of any impurity phase. And then similarly, we have also synthesized this TB2NiMNO6. So TB2NiMNO6 also there is no signature of impurity phase. So data is as flat as possible. Then we have characterized the room temperature, X-ray and neutron again. So when we do, as Dr. Adroja have also mentioned, that when we do the normal refinement, we could see in case of refinement, this is the situation. It means there is a model is not correct. The observed data is getting fitted only when we apply the anti-site disorder. Anti-site disorder means there is a disorder between CO and MN site, means CO site and MN site there is a intermixing, and because of intermixing there is a disorder, and this disorder is typically of the order of 10 to 15%. So 15%, so which we could using analysis also, and then we have not done the XAS, but using X-ray and neutron we could find that there is a disorder. And so this is the structure which we have determined from using TB2CMNO6 and TB2NiMNO6. And when we analyzed the SEM data shows that samples are, having a boundary, grain growths are there, and then typically grain boundaries are there. So that is just superficial study. And when we carried out the low temperature neutron X-ray diffraction is basically to give you, or we have tried to identify, is there the whatever phase has formed, how strong or how stable that phase is. So we have carried out the low temperature X-ray diffraction, and we could see the phase is stable. There is no phase transition. So this is stable down to 10 Kelvin. And similarly, we have seen that for TB2 and IMNO6 also phase is stable. So there, using low temperature X-ray diffraction, we could see there is no phase transition. So phase is stable, and there is no option of having impurity phase also. So using analysis of X-ray, we have seen that there is a cell parameter variation. So lattice parameter A and C varies like this. This is not following any linear behavior. So you can see that around 100 to 150 there is a discontinuity, kind of discontinuity in A. So this discontinuity is basically coming, why it is coming, and in TB2 and IMNO6 also there is a discontinuity in A. So this discontinuity, you can see the reason somewhere here in the magnetic property. So for TB2 CMNO6 we could see there is a ZFC FC which shows that there is a at 106 the ordering temperature is there. We have also seen the signature of negative magnetization. So negative magnetization, there is a possibility that in TB2 CMNO6 CO and MN two sublattices are there. So there is a possibility that we are still trying to figure out whether this is possible or not, that CO and MN sublattice, one sublattice is predominant, and because of this is dragging to negative magnetization. But when we increase the measuring field, say from 100 ostet to say 100 ostet to higher field, so we could see that negative magnetization is going towards higher, I mean it is not now negative, it is going positive. So this the negative magnetization is getting erased, and then at higher measuring field we could see the magnetization is getting positive again. And then similarly when we looked into chi inverse versus T, so we could see there is a possibility of Griffiths-like phase, because chi versus T is chi inverse versus T is following similar behavior which is seen in Griffiths-like phase. But when we carried out this is in case of TB2 CMNO6, but when we looked into the similar kind of feature in isothermal magnetization, we could see that isothermal magnetization shows large hysteresis kind of loop at 4K, which is showing ferromagnetic ordering. This is also confirmed by the analysis of chi versus T behavior, in which we could see the theta p is positive. So this is showing similarly that this is having ferromagnetic ordering. So ferromagnetic ordering is seen in M versus H behavior also. And from specific heat also we could see that ordering is seen in specific heat also at around 106 or so. So that is confirmed by the specific heat measurement. And then we have carried out similar behavior study on TB2 and IMNO6. So TB2 and IMNO6 we don't see any signature of negative magnetization in FC behavior, I mean in ZFC. But the signature of Griffiths phase are also not seen. So by just changing the nickel to cobalt, we could see there is drastic change in the magnetic behavior. So in case of TB2 CMNO6 we are seeing Griffiths-like phase. In case of TB2 and IMNO6 we are not seeing that Griffiths-like phase. So, and we have carried out, I have not shown the data over here, but we have carried out the XPS study which confirms that Ni is in 2+ state and CO is also in 2+ state. Mn is in 4+ state in both the cases. So the Griffiths-like phase was not seen. So we were really interesting to see that what is the behavior, cobalt and nickel, what is the possibility that it is showing this kind of drastic behavior in magnetization. So then we have carried out neutron diffraction analysis or neutron diffraction study we have carried out. So we could carry out up to 3 Kelvin. So you can see at 300 to 3K the peak, this peak which was there at 300K is getting enhanced. So this is showing signature of ferromagnetic ordering. So this is the case for TB2 CMNO6, and this feature which is coming at 3K, this is predominantly because of TB ordering. So TB is a rare earth compound which gets order below 10 Kelvin. So this if this is not giving the long range ordering, this is kind of short range ordering only. And when we carried out the neutron diffraction for TB2 and IMNO6 also, we could see that this is again showing a similar kind of ferromagnetic behavior. and we have temperature dependent also we have looked into it, and then as I mentioned that 3K behavior is coming only at 3K in case of TB2. CM106, this is showing the TB ordering, and TB2 and IM106. So I have not shown here, but the analysis, then we have looked into the bond distances, TBNI and TBCO bond distances, and NIO and COO bond distances. So they bond lengths and bond angles are showing peculiar behavior, which are giving rise to this kind of change in the magnetic behavior. And if I look into the conclusion, then we have characterized, we have synthesized these two compounds in the single phase, which were not reported single phase in most of the literature. So we can say that we could synthesize these compounds in single phase, and then DC magnetization shows peculiar behavior in which TB2CM106 shows the Griffiths-like phase, and then showing negative magnetization. We have we submitted this paper to the reviewer, and then though one reviewer said that there is a possibility of instrumental error, so but we have again tried, and instrumental error was nullified. So this is genuine behavior. So we are now still of the view that CO and NI bond distances are playing significant role microscopically, we can say, though I think we may not, we may have to further study this compound, and it is part of continuous study. And with this, I thank you very much. And after that, this is the acknowledgement, and then as I mentioned that these facilities are open to all the universities user. You can visit our website, and in the user portal, if you go, then all the facilities listed in all are listed for all the 4 centers. So that may be useful for you. You can take a pic of this, and if you want to contact, you can contact our Center Director, Dr. P.D. Babu, or you can write to any of the scientists over there. So that with this, thank you. If you have any question, query.
Any question? So he has nicely explained the...
Yeah, Adhoja sir have some. No, for TB2 CM106, there is only one ordering temperature. We could see from M versus T and specific it also. This is 106. And similar is the case for TB2 and M106. The ordering temperature is same. But we are expecting that locally there is a possibility that they are ordering at different temperature, which we could not identify using our technique. So maybe we need to have some specific technique which can tell, because when we are seeing the signature of negative magnetization in TB2 CM106, so there is a possibility of the cobalt and Mn sublattices are behaving in this way, that one sublattice is driving this to the negative direction. So that is possibility because of CO sublattice, because if we look into the TB2 and IM106, in TB NIMN sublattices are there, but it is not showing any negative behavior. So only CO sublattices is giving this kind of role. So basically for TB we have not fitted the, because this is not giving any long range ordering, so that we have not fitted. But for CO and MN we have fitted using this magnetic model.
Okay, so just fit it 2 times.
Yeah. So I have not shown the magnetic spin how it is showing, but this in case of TB2 CM106, these are linear, magnetic spins are linear, and TB2 and M106 are also linear, but they are making some angles. So that are the justification so far we are able to give, that this is giving negative magnetization.
Thanks. The other thing, you ball milling, you said you can make the nanoparticle.
Yeah.
Ball
milling basically.
Do you have this control environment like the inert gas, or otherwise you get oxide? Once you mill too much time,
basically,
you get oxide.
Ball mill can be used for stable compound. Like suppose we have oxide, so they are very stable. They will not get modified in terms of ball milling. So when we are doing ball milling of oxide compound or similar kind of compound, we do in steps. So not ball milling for longer time. So we take a break, 20 minutes or 30 minutes, then take a break. It will get cool down, and then again ball mill it. So step by step we'll go.
You do in the air?
Yeah. Yes.
Thanks.
Yeah.
Any other question? Any query? I have one query and one question.
Yeah.
You are measuring the magnetization AC susceptibility in the presence of a DC field at different frequencies. That facility is there?
That AC magnetization we have not carried out. That is one possibility which we can. This is whatever
No,
we have.
not on your sample. General facility.
Achha, okay, AC susceptibility. Yeah, we have.
In the presence of DC field?
So we have PPMS. So PPMS is basically having AC magnetometer. So which can have different frequency. We can have frequency from 10 Hertz to 1000 Hertz.
That's good.
And then we can apply the DC magnetic field because this is PPMS. So external magnetic field is not a problem.
Okay.
Yeah.
No, it's have anybody measure this kind of thing?
Yeah.
Because I need to study one kind of a single
Most
ion
welcome.
magnetism in
Definitely.
Second is that in your sample, your chi-square value is very large, which clearly indicate 8 point something or 9. Generally, we expect it should be less than 2 or so.
No. So chi-square is basically goodness of fitting parameter.
Yes, that's what I'm telling you.
So in case of neutron, this is slightly higher because it depends. Chi-square value depends upon signal to noise ratio also. So the signal to noise ratio, if data is slightly noisy, because sometimes TB when we are using it and cobalt is bit neutron
absorbing. Even your XRD also, the chi-square value is very large.
Just a minute.
Anyhow, you check that.
Because we basically looks into the apart from chi-square value, we look into R values also. So R values should be precisely there.
एक टेबल दिया था आपने ना नहीं
ये ना नॉट हियर
उसके ऊपर इससे पहले लीव इट
अच्छा सर इसका बोल रहे हैं
हाँ 6.99 is almost very large in
so
that
this is basically X-ray data. This is quite large, but somehow the signal to noise ratio, because as I mentioned, we have carried out this X-ray diffraction on our tabletop instrument. So tabletop instruments are good for just looking into the phase purity, not very good for analysis. So that's why it is large.
Okay.
Yeah.
Any other question?
Yeah, good.
As you have said that the neutron scattering happens, then how the neutrons generated because they are inside the nucleus?
Yeah, so basically as I mentioned this at BRC this is neutron reactor. So neutron reactor means when you have uranium-235, this is nuclear reaction. So nuclear reaction, when you have nuclear reaction, uncontrolled nuclear reaction, so you will generate 3 neutron, and those 3 neutron will helpful in extending this in a chain reaction. But if you can control the chain reaction by controlling the by controlling the neutron, that only out of 3, only 1 is going for maintaining that chain reaction.
I know about this process. Is there any way other than this?
Other than this spallation source, as Dr. Badroja has mentioned, spallation source basically you have to have a very high Z element on which you can allow the high energy particle to fall, and then in terms of that neutron will come out of that high Z element, and then yeah. So these are pulse-based neutron source. So in pulse-based neutron source, you will get the neutron in terms of pulses.
Coulomb barrier.
Yeah.
And once you cross the Coulomb barrier, then the nuclear reaction will take place, and neutron will definitely come out.
Yeah.
That's what the process. I think so.
Yeah.
जो मेरी MSc की physics कहती है, वो इतना की कहती है ना?
So these two.
So I think the longer discussion can be done during tea time. And so, if there is no question, let's thanks Dr. Kaushik again.
बाद मेरा सेशन यही है, उसके बाद कोई और होगा तो मैं क्या
Next, Venkata Srinivas Pali.
Sir.
Yeah. Dr. Venkata Srinivas Pali. He is accomplished with a material research scientist, currently works at Smart Nano Material Solution in Florida, USA. Their extensive academic background includes Master in Engineering in Ceramic Materials from Auckland University of Technology and PhD in Chemical Physics from University of Puerto Rico. Their career highlights includes roles as a senior researcher at Wright Patterson, AFRL, and a postdoctoral fellow at University of Texas and Tulane University, specializing in growth of ferroelectric, ferromagnetic thin films and lithium-ion, lithium solid batteries material. They are dedicated to next generation energy storage, a prolific contribution to the field. They have authored 80 international journal articles and 10 book chapters and have a prominent publication in Nature Electronics. He also recipient of prestigious National Research Council NRC Science and Technology Fellow Award. I request Dr. Venkata for presenting the smart materials nanostructured for multifunctional applications.
Thank you, sir. Good afternoon, good evening, everyone. As sir said, today I am talking on nanostructured materials for multifunctional applications. I belong to Smart Nano Material Solutions, Orlando, Florida, USA. Basically, I am from Hyderabad. So this is the outline of talk, introduction, problems and challenges, motivation and experimental procedures, and a few of our results which have done in a couple of years back, and conclusions and acknowledgements. So there are different types of nano particle synthesis methods available in the scientific community, as everybody is towards nano these days. So these are the different types of growth techniques: co-precipitation, hydrothermal synthesis, solvothermal, solidal, microwave synthesis, etc. So size of the particle definitely matters when it comes to the device applications, as size of the particle significantly differs from properties witnessed from the top of the micron sized particles to the top of the nano sized. So initially they used to call ultrafine particles or bulk materials or micron sized particles. Then nowadays everybody is calling nanoparticles. So various particles we made at our laboratory in USA. So basically I was working on different types of perovskites. As Kaushik mentioned, the basics of perovskites, I don't need to go into the deeper. So these are different types of techniques we have used. Interestingly, solvothermal synthesis, so where we have made size control and shape control nanoparticles, which are around less than 10 nanometer size particles. And as you all know, we can grow around 100 to 150 nanometer size soldier synthesized nanoparticles, which we were grown. and using the pulse laser deposition technique, we have grown different types of perovskites and as well as spinel structures for our different types of applications. So as you know, the conventional synthesis has micron-sized particles. The bottom figure, you can see the size of the particles when it is compared to the solvothermal synthesis. So we can control the size and shape of the nanoparticles. These are based on perovskites. So as I said, different types of perovskites were made using the barium titanate and different dopings and different substitutions using the barium titanate. Basically, I was working on lanthanum doped barium titanate and as well as barium calcium titanate and barium zirconium titanate, which was my thesis compositions. So this is called pseudo MPB composition. Which I was working on both thin films and as well as ceramics. So we were made the barium strontium titanate nanoparticles using solvothermal synthesis, which is also, you can see the very interesting and almost all the sizes of the particles were uniform, which were taken using the HRTEM at our university. So as I said, like we also made some TiO2 nanoparticles for the photocatalytic applications. So then we have done some work on polymers using the barium titanate nanoparticles, which is commercially available barium titanate nanoparticles. We have taken the PGMA. PGMA stands for polyglycidyl methacrylate. So we have used surface initiated atom transfer radical polymerization technique to grow the barium titanate based core shell nanoparticles using the polymer. So you can see the interesting TEM image with a 20 nanometer size core and shell structure using the TEM. So which we have basically used for these. We made the thin films. Once the nanoparticles are grown using the surface initiation polymerization, we have made the solution casted thin films. Then we have measured it for energy storage applications. So then we have also taken the PMMA, polymethyl methacrylate, using the barium zirconium titanate and barium calcium titanate. So those are the nanoparticles used made using the sol gel synthesis. So then we have done the same surface initiation, so using the grafting technique. So we can see one of the prominent 20% of DBCT with the PMMA. So you can see the interesting diamond shaped nanoparticles using the TEM. So this is our one of the 2 years back we have published in Nature Electronics. We have grown aluminum scandium nitrate 7030, so which was got wide number of citations, around like 75 as of today. So which is going very good. So when I was working at the AFRL labs in USA, so I was part of this. We have grown the films using RF sputtering and as well as PLD. So one of our PhD junior, Dr. Dhiren, was the leading person to grow these films. So we have done part of the work. So that's how I was also included in the work at AFRL. AFRL means Air Force Research Laboratory, which is located at Dayton, Ohio. So this is our the PGMA and barium titanate nanoparticles TEM image, which was got placed into the journal of cover. So then way back in our PhD time, along with Dr. Professor Neeraj Panwar, who is my best friend. So we have done some barium titan, BFO, bismuth ferrite, different dopings of bismuth ferrite using the rare earth compounds. So then we have this is also got into the place into the journal cover. I was one of the part of this work, and I am thankful to Dr. Neeraj Panwar. So these were soldier synthesized films. So then, as I was talking about morely, we have done the thin film work. So different types of chemical deposition, CVD, physical vapor deposition, pulsar laser deposition techniques were available in the R&D and as well as in commercialization. Basically, universities use PLD technique to grow the films. for different applications, as I was only concentrating on the PLD. So PLD is a versatile technique which is developed early in the 1960s. The first film was deposited using the laser by Smith and Turner, etc. in 1965. The first laser as a pulsed laser was invented by T.H. Maim, and the PLD is a very famous vacuum deposition technique, so which is used to grow high quality thin films. So PLD is a process which the material goes from condensed phase to that of the vapor phase, and then it comes back to the condensed phase in thin film form on a required substrate. So uses high quality power laser pulses, as you can see the cartoon diagram of PLD. So highly luminous plume comes from, as you can see, the highly luminous plume comes to the substrate, and this is a substrate, and this is the target material, which is usually we make the ceramic target, 2-inch target, depending upon the instrumentation. So highly luminous plume expands rapidly away from the target surface. Target means ceramic target. When high power laser hits the target surface, it deposits it on the substrate. So ablated material will be collected on the substrate, and it condenses, and thin film grows on the substrate. The beauty of PLD is complete transfer of stoichiometry of the material from ceramic target to that of the thin film is deposited on the film. PLD can deposit almost all different types of materials. So the versatility of this technique is more than 150 different types of materials can be grown on required substrate. Conceptually and experimentally, simplest among the other deposition techniques, as I said, like the PVD or CVD. So as I said, I was mostly concentrating on the barium zirconium titanate and barium calcium titanate pseudo cubic perovskite material, so which has got prominent piezoelectric properties around 620 picocoulomb per Newton. So which was published in 2009 in PRL. So then onwards, a lot of research is still going on that material, particularly the MPB composition with 50-50. So in my thesis, I have chosen from 0 to 100. So ceramics and as well as thin films, mostly concentrated on the MPB composition 50-50. So this is, as I said, like MPB composition has phase coexistence, that is the rhombohedral phase for the barium zirconium titanate, and tetragonal phase for the barium calcium titanate. So that's the reason we are calling it as phase coexistence at room temperature. So we are calling this as morphotrophic phase boundary material with very interesting piezoelectric properties and as well as ferroelectric properties. So as I'm skipping, as this is already talked by Dr. Kaushik. So different types of at different phases, we can see the perovskite barium titanate material is in cubic phase at room temperature, which is in tetragonal phase. Then it is, when it is coming down to the around the 0 degrees centigrade or 5 degrees centigrade, it is orthorhombic. Then it way beyond, if we go down, it will be in rhombohedral phase. So different types of perovskites were there. So such as barium titanate, PZT, PMNPT, PLZT, which are commercially used for piezoelectric applications, especially the PZT and lead-based materials. But however, most of the countries, they have restrictions on PZT, especially Europe. So, but still the research is going on. There is no substitute for the commercialization of this material. So people are coming up with the barium zirconium titanate and barium calcium titanate as a substitute. But however, it has got its limitations, like the low TC for this material. So, but still working on different aspects of the properties of the materials. So we can see the lithium niobate, such as lithium niobate and lithium tantalate, bismuth layered oxides. One of my senior is talking on the other session on the layered oxides, the O12 and O15 compositions. So compounds containing these are the early day ferroelectric materials, organic perovskites, like as I was talking about PVDF and its polymers and copolymers, so which were also very interesting for application purpose. So ceramic polymer composites. So as ferroelectrics and antiferroelectrics are extending polarization saturation to high electric fields, so my thesis was mostly concentrated on ferroelectric energy storage. As you can see, the polarization versus field or voltage. So the shaded area is the energy density which is coming from the topmost curve, that is called discharge curve, and the bottom curve is called charge curve. The inner area is the energy loss. So this is the basic mathematics. We can that's how we calculate the energy storage of the materials. So the energy storage, the units for the energy storage is joules per centimeter cube. So then I have taken the 50-50 morphotrophic phase bond decomposition for the epidaxial growth and as well as the polycrystalline growth. Here I am discussing on the epidaxial growth of the BZT-BCT compositions. So as I said, like we have taken the basic oxides to prepare the ceramic target, and then we have used the solid state sintering road to make the ceramic 1-inch target. So then PLD grown thin films were obtained using this composition. So this is the cartoon diagram for the, as I said, like we have used different oxides, and this is the flow diagram for the making calcination and all. So how we have mixed the oxides. Then for basic structural characterization, we have done the XRD and Raman spectroscopy. As I'm sorry to forgot to mention, as my supervisor's name is Dr. Ram S. Katiyar. So he is specialized in Raman spectroscopy. So our basic characterization will definitely include the Raman spectroscopy for each and every material whatever we make in the laboratory. So then we have sintered the ceramic target at 15 to 1600 degrees centigrade. So to obtain the phase purity of the material, then the same target was used for the PLD growth. We have, as I said, like we have used the MgO substrate to, as MgO is not conducting, so we have used LSMO, a perovskite LSMO as the bottom electrode, and as well as it is a conductive substrate, a conductive material. So we have grown LSMO on top of the MgO. So then we have used the ferroelectric material, and we have grown that, and we have optimized the different parameters to obtain the phase pure material at around 700 to 730 degrees centigrade. So as I said, then once we have got the films, when we have done the Raman and XRD, Raman and AFM and PFM studies. So then we have using the DC sputtering, we have done the electrical dots, where we have used shadow mask to deposit the dots for the electrical measurements. So this is how we have gold as the top electrode, and as well as, so as I said, like for epitaxial growth we have used gold as the top electrode. For polycrystalline films we have used the platinum as well as top electrode and as well as bottom electrode. So as you know, the platinum silicon, the bottom electrode itself is the bottom, platinum itself is acting as a bottom electrode. So then we have done the ME coupling studies on these materials. So that is, I'll talk, we have taken, because as multiferroic materials are limited at room temperature, so single phased, so we have developed a artificial multiferroic material, like using this BZT-BCT composition with CFO and NFO, and tri-layers and different layers of films were grown. So that's the reason I call it as artificial multiferroic material. So these are the optimized parameters for deposition of the films. The films were grown at this energy, and as well as temperature is 700 to 730 degrees centigrade. So this is the substrate temperature, and this is the annealing temperature of the material. So as I said, like LSMO is the bottom electrode and gold as the top electrode using the shadow mask. The substrate is MgO, and the surface and target distance is the main component in obtaining the film quality in PLD. So we have taken 5 centimeters as the substrate to target distance, as shown in the cartoon diagram. So then for electrical measurements we have done the, we need the metal insulator metal configuration. So as I said, like these are the substrate and bottom and top electrodes. So this is how it looks like that. So then the basics of the XRD for the bulk BZT-BCT material. So from the XRD, you can see that the phase pure material was obtained. So then we have done the thin film XRD. So one more interesting here is we have these films were went up to 10 power more than 10 power 12 cycles. So from the image you can see that this is before cycling, means at room temperature we got the XRD for the material. So after 10 power 12 cycles you can also see there is no degradation in the XRD. So that is how it shows the quality of the material. So then we have done the Raman measurements at before cycling at room temperature and after cycling at room temperature. So which also shows the prominent peaks for the perovskite AbO3 structure of the material. So which also confirms the ferroelectric nature of the materials. The signature peak is around 305 to 3010. So that is prominent for the AbO3 type of perovskites. So then we have done the bulk ferroelectric measurements at room temperature at different kV per centimeters. So which is showing interesting ferroelectric behavior for the bulk. And as well as the thin films at room temperature, as we can see, we went up to 90 volts, but when we are going to up to after 70, so there is a little expansion in the loop. So we are confined to up to 70. So after 10 power 12 cycles, we have done the fatigue testing for this material. So which also shows interesting ferroelectric loops up to 70 volts. So interesting ferroelectric loops. As I want to mention, we have applied for a US patent on this material for this fatigue studies, and as well as the photo response studies are also done on this material. So as you can see, the fatigue for the up to 10 power 12 cycles, we can go beyond the 10 power 12 cycles, but we don't want to break the sample. So we have confined up to 10 power 12 cycles. So then we have done the piezo response force microscopy studies on this material, plus or minus 12 volts, which also shows the square patterns with the bright and dark contrasts after 10 power 12 cycles. So as I said, like nanoscale switching and the square patterns with opposite voltage confirm the ferroelectric and as well as piezoelectric nature of these materials at nanoscale. The interesting part is after fatigue studies. So then we have done the room temperature dielectric versus capacitance versus voltage, and then we have calculated the dielectric constant, which is also showing interesting dielectric constant values at room temperature at different frequencies. So you can see the loss is very a bit high, but still it is showing interesting properties. So then we have obtained the optical measurements for this material, which is also showing interesting optical properties for the band gap with 2.7 for this material. So we can see the NGO substrate and as well as the material here. So the interesting stuff is like the energy band gap is low. So that is what made our interest. So then we have done the photovoltaic and as photo response studies for this material. So I'm not going into the details. So these are the photo response studies of the material. So the interesting current versus voltage studies were made due to the experiment. Due to the instrumentation limitation, we went up to only 500 cycles for the current versus field. So as you know, these are the basics for the resistor behavior, how it behaves when you take the IV measurements. This is the resistor and voltage source behavior for any material. So how the Schottky diode behaves, and this is the overall different IV characteristics for the material properties. So as I said, like interesting as we have done in dark and photo modes. So you can see the interesting current density versus field loops for the material. So then we have done the photo response studies for this at different powers. So which is also shown interesting properties. We have done at 0 field and as well as 0 voltage and as well as 20 volts. So 0 voltage is the most important for the self-sustained material for applications wise. So then we have done the, as I said, like we have done the artificial multiferroic properties for the materials. So as you know, we have used we have scarcity of single phase multiferroic materials, so we have used artificial multiferroics. So that then I'm not going into the deeper into the subject. So then we have these are the challenges for the single phase multiferroic materials at room temperature. So only BFO, which was well explored in last 10 to 15 years or more. So but still it has got its own limitations because of the high leakage current behavior. So then we thought of how about artificial multiferroics. Then we have used the ferroelectric component and as the BZT BCT and the cobalt ferrite as the ferromagnetic magnetostrictive material. So we have used as the magnetic component, and we have made the trifilms using the PLD. So this is the spinel structure. I am not going into the deeper into the subject. So this is again the platinum silicon grown ferroelectric films. On top we have done the CFO, so platinum silicon substrate. We have done the insulating material deposition, then CFO deposition, and again on top of that we have done the BZT BCT deposition, and we have done all the structural and electrical characterization measurements, which were also shown interesting properties at room temperature and as well as temperature dependent ferroelectric and as well as ferromagnetic properties. So as this is these are the parameters for the ferroelectric component deposition and as well as the CFO. So as I said, like we have used the metal insulator metal configuration for the electrical measurements. So then these are the properties for the ferroelectric thin films. This is ceramic target, which you can see the phase pure ceramic target, and then the BZT BCT films at room temperature. So using the platinum silicon substrate. So then on platinum silicon substrate only we have done the CFO at 600 degrees centigrade as the deposition temperature. So the combination of both artificial ferroelectric and CFO and BZT BCT tri-layers, you can see the required phases for the material. So this is the room temperature at different frequencies. We have done the polarization studies, which are also shown interesting ferroelectric properties, and the room temperature magnetization for the tri-layered films. So then we have done the temperature dependent MH studies. So this is done on the lakeshore vibrating sample measurements, so VSM measurements. So but this is obtained on squid using the small piece of film. So then we have done the different ferroelectric measurements at different temperatures at different at specified frequency, which is around 4,000 hertz. So then we have done the room temperature capacitance versus field measurements, which is also showing interesting dielectric constants with respect to temperature. And so these are the current versus voltage measurements for this film. So then we have done the magnetoelectric coupling studies for this artificial multiferroics, which is also showing interesting ME coupling behavior, showing hysteresis behavior for this material thin films. The widening in the loop is due to the coercivity of the CFO phase, and the positive ME values is due to the remnant magnetization of the CFO phase. A maximum of alpha 63 ME centimeter oversted is obtained at a maximum field of 7 kilo oversted. So as I said, like for the tri-layered films, we have done the PFM measurements, so which is also showing interesting square patterns at room temperature. So with plus or minus 9 volts, I suppose. So then we have done the hysteresis measurements at nanoscale, which is also showing interesting hysteresis phase and amplitude properties for this material. So at different places of the thin film. So then we have done, as I said, like we have interesting square patterns with both ferroelectric and piezoelectric behavior of this material, which confirms the ferroelectric nature at room temperature with plus or minus 9 volts applied on the film. We have done it using different instrumentation. So that's why this is at using different instrumentation, and the other one is basic instrumentation at our lab. So this was done at Professor I don't remember his name, but he's from University of Nebraska, Alexei Gruberman, sorry. So in conclusion, lead-free barium zirconium titanate and CFO barium zirconate tri-layered thin films were fabricated using PLD technique. Excellent multiferroic behavior with high saturations of and high polarization as well as saturation magnetizations. Excellent ME coupling behavior was obtained, and the electrical and magnetic domain patterns were visualized using the PFM and MFM studies. So nanoscale switching and square patterns with opposite voltage confirms the ferroelectric and piezoelectric nature of films at room temperature. Tri-layer nanostructure were applicable for multifunctional applications. So I got an opportunity to work with Professor Douglas B. Chrissy, who is expertise in the PLD. So who wrote this book around like 35 years back, who edited this book. So this is Dr. Chrissy and this is myself. So don't compare me with that photographs to me as of now, my current state. So this is our PhD group. This is Dr. Ram Eskatiyar, so who is my PhD supervisor. He is a direct student of Dr. R.S. Krishnan. R.S. Krishnan is the student of Dr. C.V. Raman. So this is our group. I think you can identify this. This is my best friend who is sitting here, Professor Neeraj Panwar, who is the convener, who is the secretary of this conference. So thanks, Neeraj. So just I want to remind you those days. So this is our group at University of Puerto Rico. So these are our collaborators, both in India and as well as in USA and somewhere else. So I would like to acknowledge the conference chair and as well as whoever is part of this conference by name and everyone. And special thanks to my dearest friend Dr. Neeraj Panwar, Department of Physics, Chaudhary, Charan Singh University. And thanks for the opportunity. So thank you.
Dr. Droja.
We are doing some 10 to the power 12 cycles.
Yes, sir. Yeah.
How much time does it take those more cycling?
Yeah, I was more or less I was spending 1 week time in the lab, which was done at AFRL lab in Dayton, Ohio.
So you give the number of automatic cycling, just go.
Yeah, I put the cycle. I requested one of our postdoc to sit when I went for nature calls and all. So I was continuously running the.
And with those cycling, first cycle, end cycle, results are same, or you just change something?
Yeah, that's what the beauty of the films, as I have shown, both ferroelectric and as well as XRD Raman, before cycling and after cycling, which shows the quality of the films. There is no deterioration from the room temperature to that of the after cycling. So that is what the beauty.
And also, do you study the interface effects?
Interface, we have not gone through that.
Surfaces.
Yeah, surface interface. Yeah.
Thank you.
Thank you, sir.
I have one query. You are using LSMO for the bottom conducting layer, but it is ferromagnetic in nature. So does it interfere in your system and getting any kind of electromagnetic coupling?
That's an interesting question, but we have not completely studied on that
Because
one.
generally we are also working in multi-layer system. There we need a bottom electrode. We use a strontium ruthenate, which is again a very nice metallic system but non-magnetic.
So you have to tell, sir, as I'm a student like you, a student before you.
No,
so
no,
we
no,
should, we
you
should
are not student, you are my colleagues and I respect you.
I'm also curious to learn from you that whether it will be the effect of LSMO or the CFO. So you should.
Because CFO Ramesh has published one very nice paper with the barium titanate and CFO composite system.
On science paper, yeah.
Yeah, science paper. That is a very old time. Any other question? If there is no question, let's thank the speaker again.
I request Dr. Neeraj to come onto the stage. Thank you, sir. Thank you very much, sir. Thank you.
Oral. So now I will invite Mr. Gurpal Singh from Oxford Instrument Plasma Technology for plasma etching and deposition technique. His topic on the topic. He will give an oral presentation of 15 minutes.
Hello. Okay. Good evening, everyone. So I'm from Oxford Instruments, and plasma technology is one of our division. So first of all, I'm really pleased to see that these important conferences are really now coming to the universities. So usually, we see a lot of these conferences happening at IITs or the tier 1 institutes, but now it's really spreading across. And as soon as I saw this happening here, I was really pleased and share some insights on the plasma etching and deposition techniques. So I'll quickly give you a brief intro about Oxford Instruments, and then I'll show you different plasma etching and deposition techniques. Okay. So Oxford Instruments is a UK-based company. We are first commercially successful startup of Oxford University. That's how the Oxford name comes. It was maybe 65 years ago, and mainly we have two divisions. So one is imaging analysis. There we make AFM, Raman, and some imaging solutions. And then we have the advanced technologies group. So where we make the equipments which are used into the fabrication of semiconductor devices. So those are front-end fabrication equipments, and these are the equipments we will be talking about today. We do about $500 million in revenue, and we are present globally, about 27 locations in 23 countries, including India. Our India office is in Mumbai. I'm based out of Delhi, so we have site offices in Mumbai, Bangalore and Delhi, and then head office is in Mumbai. And Then we cater three major markets. So one is material analysis, which is served by our imaging and analysis group, and then semiconductor market, which is served by the plasma technology group, and then we have healthcare and life sciences market segment, and of course we sell some equipments into the traditional R&D markets, and including quite a lot of things for the quantum technology. Okay. So this is our headquarter in the UK, where we make all these plasma equipments. So when we talk about plasma etching and deposition, so we just don't etch or deposit the film. So we solve one of the challenges, right? So typically it could be the removing the damage. So when you have your substrate, maybe coming from the polishing or coming from some of the previous processes, it might have some subsurface damage. So there are ways to remove it using plasma etching techniques. Then second thing is very, very important, especially for the photonics applications. You really want your interfaces very, very smooth and defect free. And when you are depositing one material on the other material, you want to ensure your interface is really, really good, and that results into a good device performance. And then also for some of the photonics devices, where you really need to make the slanted grating. So typically, if you look at all the traditional techniques, plasma etching techniques, so they are vertical. You cannot make slanted gratings, but there's something called ion beam etching. Using that, you can make the slanted grating, and that has a very, very specific application. So if you have seen the big headsets, virtual reality headsets, so those headsets would use one of these processes. And then of course your CVD processes and the ALD processes. So ALD is traditionally seen as a very, very low rate process, but we have a way around it, and we can deposit at quite high rate. Okay, and this is quite desirable for the superconducting and quantum researchers. So when you are going beyond a certain number of qubits, you need to stack it into the 3D, and that's where you need really, really high speed ALDs to make these superconducting wires to stack your qubits into 3D. So when we talk about etching techniques, so there are fundamentally a couple of etching techniques. So they vary on, depending on your application requirements. So if you want a very, very high rate etching, where you want to go through the wafer, make through silicon vias, you use a deep reactive ion etching kind of process. So it's a Bosch process, and it runs a cyclic process, which is etch and passivation, and with that you can go down to several hundred microns. But whereas if you want a very, very smooth surface and you do not want any damage, then you switch to atomic layer etching. So really you are removing here a couple of angstroms every cycle, and you go very, very slow, and everything else is in between. So how these techniques compare to each other? So if you look at the cross section, so RI is basic parallel plate capacitively coupled type of plasma system. You have your shower head, gases comes through top. You apply your bias to the table, and you sit your wafer on the electrode, and that gives you some sort of etching. There are not a whole lot of chemistry available. It's mostly sputter etch. You induce a little bit of argon into the chemistry, and that gives you the ions into the process, and you end up etching some material here, right? But as you want to go a little smoother, and you want to have a low damage etch, then you switch to the ICP process. So here you have basically two sources. So you have your ICP remote source, and then you have your bias. Okay, so your wafer sits here, plasma gets generated remotely from the wafer. You apply a couple of 100 watts of ICP power, you bring your gases, and your plasma gets generated here, and then you apply the bias as you require. So basically you have two controls here. You have your ion density control and ion energy control, and this enables you to do a very, very smooth etch and very, very controlled etch. So if you want to control your profile, your roughness, you need to switch to ICP. All of that is not possible into a typical RIE system. And if you want to go a step further, then you switch to a ALE process. So ALE and ICP, basically it's the same system, but its additional attachment comes on an ICP system. And this is a cyclic process again. And when you etch with the RI, so your subsurface damage is down to maybe 15 or 20 nanometer, whereas with the ICP, your subsurface damage is about 6 to 7 nanometer. And if you really want to get rid of that damage, you need a process where you have a sequential process when you are having your chemistry working and when you are having your ion. So you basically cycle your bias power and your gases, and that way you bring your subsurface damage to sub-nanometer level. So you can control your subsurface damage down to 0.5 nanometer, and also roughness can be down to 0.1 nanometer or 0.2 nanometer levels. And of course, DRI is only used for silicon etching, very, very deep etching. And ion beam etching is used for a slanted grating etch or some of your laser, some of your optics related applications. So you have your substrate mounted on your platen, and then you fire an ion beam gun here, and by tilting this you can etch at a tilted angle, or you can etch it vertically. So that gives you a very, very good control on your gratings, slanted grating angles. So these were the etching technologies. And when we talk about the plasma deposition techniques, previous speaker explained very well about the PLD technique. So PLD technique is one of the technique, but when we talk about the plasma deposition technique, so there are several plasma deposition techniques. So it starts from PCVD and then comes down to the ALD. So if you want to deposit at quite high rate, you use the PCVD, and if you really want to grow layer by layer, then you switch to atomic layer deposition process. And ICP CVD and IDB ion beam deposition would be in between. Right. So when we look at these four different technologies, so PCVD is very much like a RIE, but the configuration is reversed here. So in the RIE, your electrode is the table is biased, but here your table would be grounded and your shower head would be floating, and then again gases comes from the top, and gases would be the deposition gases in this case, and it gives you quite high rate deposition up to 1 micron per minute kind of deposition rate you can get on an oxide, maybe several hundred nanometers of per minute rate on nitride. And typically to get a decent quality film, you need to be in the range of 350 or higher temperature. If you go below that, your dielectric would not be that good. It will be porous in nature, and the breakdown voltage of the nitride films or the would not be in order of 7 megavolts or higher. So to get that voltage, you need to be in the range of 350 plus. But if your wafer or your application is temperature sensitive and you cannot go to these high temperatures and you need to deposit at much lower temperatures, then you switch to ICP CVD. Here you can get a very good quality film down to at 100 or 80 degree temperatures. It's compared to PCVD, it's quite slow. You can get maybe 100 nanometers per minute of oxide, 15-20 nanometers of nitride per minute, but it gives you a very high quality film at much lower temperatures. So if you have a temperature budget, then you need a ICP CVD. And then if you are working on some specific applications where you are working on optical properties of the film, you really need a stack which is really low loss stack. For example, laser bar facet coatings. Then you use the ion beam deposition kind of system. You will have a pre-clean source, so it's very important. When you deposit these kind of stacks, you need to pre-clean your substrate. You fire the etching source, and you pre-clean your surface, get rid of native oxide, and then you fire your deposition source, and then you have your 4 targets, and depending on which material you want to deposit, so you switch the right target and then you sputter that material onto your substrate, and this substrate would be rotating at quite high speed to give you a very high uniformity as well. ALD is quite different process from all of these. So this is basically you grow a layer by layer material. It's a surface limiting process. You bring your precursor into the chamber, you pump and purge, and then you again activate the surface and you pump and purge. And by doing this, you grow these materials layer by layer. And if you are looking really low thickness but very high quality film, and again little bit more conformal film, then you use the ALD system. So these are the deposition techniques you can have. So I have brought, since we are talking about futuristic technology, so I have brought an example of a futuristic device. So you might have heard of all these AI enabled Meta glasses. So Ray-Ban and Meta are working on this. They are selling this into the market, quite expensive at the moment. Lenskart is also selling that, not as good as these glasses. These would be a couple of $1,000s. So if you look at this device, this really shows you that, you know, to be able to put such a device, you need to know all the domains, or at least how the ecosystem is embedded into that. So you need your photonics related knowledge to work on the lenses, which is also a lens and also a screen. Then you need your power device, which is to charge the battery at high rate. Then you need your micro LED for your screen. So really everything comes together on these devices, and you need basically all the compound semiconductor knowledge to put such a device together. So this is my summary slide. So at plasma technology, we enable all compound semiconductor related technologies, and be it a micro LED or artificial intelligence type of devices, or virtual reality type of devices, we have solutions for that. If you are working on quantum technology, then we have really high rate ALD systems, or we can etch a diamond. And etching diamond is no problem, but getting a working NV center is a challenge. And using ALE, you can really endpoint your process very close to the NV center, and which will eventually give you a working NV center. So we can enable your quantum research. If you are working on optosensors or indium phosphide or gallium arsenide based devices where the damage is key, again we have really well established processes for that part of the work. If you are working on again lasers, then we can offer you laser coating, laser bar facet coating systems, or indium phosphide etching. Indium phosphide etching is a very tricky process. You cannot do it in any ICP or any RI system. It requires very specific configuration, and we can enable that. And of course, if you are working on the power, then power or RF, then we can enable the gallium nitride or silicon carbide power devices. So be it a silicon carbide MOSFET device or GaN power device or GaN RF device, we have well established processes for that. So today we have only 15 minutes, but if any of you interested to talk about any of these techniques in detail, please reach out, or on our website there is a webinar for each of these sections, really detailed webinars, really informative. Please go through that, and it's free. You can simply download and watch it when you are free. Thank you.
Any query regarding this plasma technology? If there is no, so let us thank the speaker. And everyone has kept the time limit very nicely before even without putting pressure by myself. And let's thank all the speakers of this session. Okay, thank you. So any another talk on this session, or it's over?
we would like to request प्रोफेसर बीरपाल सर कि वो आए और यहाँ पर हमारे जो सेशन के चेयर हैं उनका फैसिलिटेशन करने का कृपा करें. So this was the last event for last session, technical session that we had. So we'll go for tea break, and we'll meet at 7 in culture program. Thank you.